Okay, it does say it's streaming.
Over here it says setting up.
Oh.
I think it's working. Yeah.
I see. I can quickly try to add it to the website, though it might take me. Never mind. Or,
Do you see the link?
yeah, I see. I can copy it. Yeah. Okay, let me try to put it on the website in the next. Okay, it's on the web page now. And I can click it. Yeah.
Sorry, excellent. I think it streams with a little bit of delay, but that's it's good to know that it works. Okay. Okay, we have 25 people except us. 26. Right. So I guess we'll try to start on time, probably, right?
Yeah,
Or
let's
we
do that.
should.
Yeah.
Okay. Right. So I assume people can hear me. It's a little awkward to not have feedback. Good. So I'll be monitoring the Q&A for questions. Generally, we'll reserve the last 5 minutes of every talk for answering questions. Again, I'll monitor the Q&A. Please either raise your hand to ask a question, at which point I can unmute you, or just ask a question in the Q&A and we'll address it at the end of each talk. And Zohar is here. Let me just... Right, so you can chat with the panelists, but please, if you just have a question, try to use Q&A instead. Maybe you can use chat if there is some technical issue. Okay, so I guess, okay, we have 2 more minutes. Zohar is here.
So
maybe we don't need to do a test for Zohar. We'll just hope it works the same we did yesterday. Okay.
Hello.
Hi.
So it says I'm sharing my screen, but I see myself. Like, do you have to click on something to switch?
I see your screen.
Oh, okay. Oh, right, of course. Yeah, that makes sense. Okay.
Okay, so I'll mute myself when you start. Maybe I can also stop the video. We already have a question whether we're going to be making slides available. I'm definitely happy to make mine available.
Sure, same here, yeah.
I think that's the idea. We'll make slides available as long as Zohar, Peng, and Aditya agree.
Yeah.
I do.
Okay. Okay, Aditya also says he's fine, and Peng also says they're fine. Okay, so we will make slides available on the workshop website, I think.
Yeah.
Okay, I think it's at least for me, it seems to be 1 p.m. So maybe I'll let Nikhil take it off.
Okay. Okay, so yeah, welcome everyone to the STOC 2020 workshop on discrepancy. So we'll have today 5 talks. So the first 2 talks are a bit longer. They're 45 minutes and a bit more overviewish. So we'll start from the basic results and sort of get to the cutting edge of current research. And the next 3 talks will be more sort of based on results which maybe came out even last year or even very recently. And they'll be about applications of discrepancy to sort of various surprising things. Okay, so that's the plan. And yeah, there will be 5 minutes. We'll try to have 5 minutes in between the talks for Q&A and a short break possible. Okay, so let's begin. So yeah, so I'll start with the overview on algorithmic discrepancy. And we look at it sort of from a convex geometric point of view and look at some basic definitions and applications. So let's dive right in. So classically, combinatorial discrepancy deals with the following setting. You are given a universe of n elements, 1 through n. And there are m sets on this universe that you are interested in. So here is a picture on the right. And you want to color these elements red and blue so that in the ideal case, each element is colored as evenly as possible. Right? Though this may not always be feasible to color everything evenly. So you want to be as good as possible. So a bit more formally, there are n elements, and we'll think of the coloring as +1, -1. So given a coloring chi of these elements, you can define the discrepancy of this coloring as you look at the maximum over all your sets S, and you just sum up the colors of the elements in that set, right? So if there were equal numbers of plus and -1, this number will be 0. Otherwise, you'll measure, this quantity will measure the imbalance. And then you look at the maximum imbalance over all sets, right? So this is discrepancy for a coloring. And the discrepancy for a set system is the best possible, like the discrepancy of the best possible coloring. Okay, so that's going to be the notion we'll use throughout this talk. So one useful way to think about this is the following. So let's say you are given an m by n matrix. So in the previous example, the rows would correspond to the m sets and the columns would be n elements. And think of this as the 0-1 incidence matrix. So you want to color the elements red or blue or multiply them +1 or -1. And you want to minimize the row sum, right? So the discrepancy, if you think in this matrix, you want to find a +1, -1 vector x. So that if I look at a times x and look at the infinity norm, that's the discrepancy. Or another way, sort of a vector balancing view, is that you can think of as given vectors, which are these columns of this matrix, say v1 through vn, and these are m-dimensional vectors. And you want to find like a signing of these, so that if you look at the signed sum, so xi vi, summation over I, the infinity norm is as small as possible. Right? So again, the same thing. And more generally, so traditionally people look at infinity norm and discrepancy, but you can look at more general norms, say given by some symmetric body K. And again, you can ask the same question. I want to find a +1 -1 coloring that minimizes the norm with respect to this body K, given by this body K. Okay. Right. Good. So one thing is, given a discrepancy problem, you can always do a random +1 -1 coloring, right? So this is always going to be like a very basic benchmark, right? Because this is always possible. But typically the problem is when you do this, do a random coloring, your discrepancy is going to grow like square root of n, right? Like n is the number of columns. So this is just the standard deviation. So even if you just had a single row, typically a random coloring would give you root n. And just as a benchmark, so let's say if you have an arbitrary set system of m sets, if you did a random coloring, you'll get a root n root log m, right? So again, root n is the standard deviation for any set. And this root log m comes because of, you apply Chernow bounds and take a union bound. So that's going to give you the root log m. Okay. So in some sense, discrepancy theory is all about, you can say, beating this random coloring, right? Like if you can't do anything better than random, it's not an interesting question. And even though we like random a lot, and often random colorings do give the best answer in many settings, but there are serious drawbacks with random coloring. So one, it completely ignores the structure of A, right? You are just coloring things without even looking at A, which may lead to very suboptimal results. And even if there is no structure in A, sometimes there are surprising results possible. So for instance, for this question that I said about arbitrary set systems, there is a very classical result of Spencer, which says that if you had, say, n sets, you can actually get rid of this root log m factor here and just get order root n discrepancy. And again, sort of a very surprising result, which really kickstarted this area. Okay, so yeah, so it's going to be all about beating random. So let me just quickly give some applications to get a feel for this. And some of these applications come in very, very surprising areas in many places in math and CS. So let me just be very brief. We'll see many more applications later during the workshop. So one sort of very generic idea, and Sasha will talk more about this later on, is that you can use sort of low discrepancy to get good sparsification, right? So there's even a name for this general principle called the transference principle. So very roughly, the idea is, suppose you had a set system, and let's say in the ideal case, there was a discrepancy 0 coloring of these points. So now if I just, let's say, restrict my set system to these red points, so intuitively what's going to happen, right? So my universe will sort of shrink to about half the size, but each set, because the discrepancy was 0, will shrink by exactly half, right? So you can think of it as, I've gotten a very good sparser representative of my set system. Like I've shrunk everything by half, but still sort of preserve the relative cardinalities and so on. And usually, yeah, so many sort of sparsification things can be cast very cleanly in terms of this discrepancy view. So for this reason, discrepancy comes a lot in like computational geometry, where you look at epsilon nets and samples, and also in machine learning. So Zohar STOC will talk quite a bit about this, like using getting better core set constructions using discrepancy and so on. Again, combinatorics, it's a natural place because you often deal with these nets and so on. Another sort of maybe surprising application, which again started in fact long ago, like discrepancy in a way originated from this application, was in quasi Monte Carlo integration. So here, usually you are given some complicated domain, and let's say there is some function which you want to integrate, but all you can do is evaluate this function, right? Like maybe this function has no closed form and so on. So the classic Monte Carlo approach is to generate a random sample in this region, evaluate your function at this point, and take an average. And we all know, like if you take about n samples, your error will decay as 1 over root n. But often you can do much better using these quasi Monte Carlo techniques. So often you can find much better placements of these points. And one way you do this is you start with a very dense placement of points. Almost think of it as like you're placing a continuous collection of points. So it's a very good approximation to your region. And then if you can find a low discrepancy coloring of these points, you can sort of iteratively use it to sparsify and get a much better placement of points, which will give you much lower error. So this is sort of one very traditional application, maybe even started more than 50 years ago. And it's a big area still in this field. So another application which we'll see later on in Peng's talk is to experimental design. So I'll not talk about it more. Let me give two quick sort of surprising applications. So one is for rounding LP solutions, which again comes widely in computer science. So there's a classic result of Lovash, Spencer, and Westergombe, which says that given any matrix A and any fractional solution X, you can round X to another integer solution X tilde. In fact, X tilde is like a floor or ceiling of these X, so that the error that you get when you round your solution in any sort of row of A is at most what's called the hereditary discrepancy of A. So I won't describe what hereditary discrepancy is. It's sort of a bit more robust variant of discrepancy, and Sasha will talk much more in detail. But roughly the idea here is the following. So imagine for a moment you're given a half integral solution, X, with satisfied AX equal to B. And if you had a low discrepancy coloring Y for your matrix A, right, then you can use the signs of this Y to decide to round X up or down, depending whether the ith coordinate was +1 or -1. And if you stare at it for 5 seconds, you'll see that, if the discrepancy, let's say, was 0, it will not add any error to B, right? So again, sort of this is a very natural connection with discrepancy, and yeah, it works in full generality. Let me just say one final application before we go into the results, which is again used a lot in integer programming and speeding up dynamic programs and so on. It's a very surprising application if you first see it. So here the setting is the following. Let's say you're given a bunch of vectors, m-dimensional vectors, v1 through vn, and let's say their length is 1, just for concreteness, Euclidean length. And let mu denote the average of these vectors, right? So summation vi over n. Now your goal is to find a ordering of these vectors or a permutation, so that if I look at the kth partial sum according to this permutation, I want it to be as close to k times the average as possible. So maybe pictorially, let's think of it. So, if I look at all the n vectors, their sum is n times mu. And in the beginning, the zeroth partial sum is 0. So as I vary k along this axis, my mean, the partial sum will be k mu. And I want this sk to be tracking this as close as possible. So again, if you did a random ordering, you would get discrepancy about root n. But actually, you can do much better. So the current best results that we'll see later on actually give you square root log n, which is an exponential improvement. And this really has a lot of applications. Okay, so the rest of the talk will be the following. So I'll start with sort of a more geometric view of discrepancy. So we'll see how sort of geometry naturally fits in. And then I'll quickly describe two very classic results in this area, which originally were non-constructive, but sort of they're very powerful. So almost every result in discrepancy boils down to some clever application of these two methods. So it's very general. And then after seeing these methods, we'll focus on sort of the algorithmic approaches, which have been developed in the last 10 or so years. And by now, we sort of almost know exactly how to make both these methods algorithmic. And these algorithms will be based on sort of variants of random walks with various kinds of enhancements, except maybe this result due to Rothfuss. And so my goal in this talk will be to sort of give some intuition about these enhancements and give some proofs and so on. Okay, and so we'll have one running example throughout the talk, just to sort of see the relative strength of these results. So this is again a very classic problem in this area called the Beck-Fiala problem, where you're given a set system where each element lies in at most t sets. So think of t as a small parameter, maybe log n or so on. So it's kind of a column sparse set system. So t column sparse. So again, given such a set system, if you did a random coloring, you would get a root n discrepancy because the row sparsity can be up to n. But we'll see that these partial coloring techniques give you already something much better. They give you root t log n. And the Banaszczyk's technique, which is sort of the best we know so far, gives you root t root log n. And the big conjecture in this area is that square root t might be the right answer. So we don't know of any worse example. And there is a much more substantial generalization of this called the Komlosh conjecture. So notice in this setting where your columns are t-sparse, if I scale everything by 1 over root t, the L2 norm of my columns is 1, right? Or at most 1. So Komlosh conjecture sort of generalizes this. It says, given m-dimensional vectors with Euclidean length at most 1, is there a +1 -1 coloring which gets you only order 1 discrepancy, right? So again, that would like generalize Beck-Fiala. And yeah, the current best we know is only order root log, basically. So maybe a couple of things. So I won't put order notation everywhere. So when I say like things like square root t, I really mean order root t, just for clarity. Yeah, so right. So there's always a constant sitting somewhere. Okay, good. So let's begin with a geometric view of discrepancy. And it's a very simple observation, but somehow very powerful. It opens up the door for applying many, many results. And the idea is just the following. So again, I was given a matrix A, and I want to find a coloring X whose discrepancy is low. So let's define the following polytope parameterized by T, which says that AX less than T times all ones vector and at least minus T times all one vector. Right? So again, maybe pictorial, you can think of it. For every row, there are these two slabs, AIX bigger than minus T and less than T. So one equivalent way of saying that the discrepancy is, or at most T, is it's if and only if P of T contains some point, some +1 -1 point, right? Because like if you look at this polytope of these feasible regions X, if there is some +1 -1 point X, I mean, that gives you your low discrepancy coloring, and also vice versa, right? So it's really a simple observation. But now this opens up doors to various things, because we can look at it geometrically and then try to understand how big I need to make this T so that this polytope P of T, like that scales as you grow T, contains some +1 -1 point. Okay. So one very classic result of Gluskin is the following. So it says if you have any convex body, not just a polytope, let's say which is symmetric and has a large Gaussian volume. So again, Gaussian volume is the standard Gaussian volume. So says that the Gaussian volume is at least 2 to the minus n over 100. So notice it's exponentially small, but still we'll think of this number as sort of being largish, which I'll make precise in a second. So the theorem states then this polytope P, then this convex body P contains some point with at least n over 2 +1 -1 coordinates. So maybe again, just a pictorial view, and unfortunately I can only draw in 2 dimensions. So if you had some convex body P with sort of large enough volume, then like this, so it doesn't have any fully +1 -1 point, but let's say if you look at this point here, it has at least one coordinate +1. So that's what it's saying. And okay, and what do I mean by like large? So if you look at this +1 -1 cube, let's see what's the Gaussian measure of this +1 -1 cube. So this will just be like, if you just the Gaussian measure of the interval -1 through 1 raised to the n, right? And this is just like some 0.68, some constant to the n. So roughly like 2 to the minus n, right? So again, cube is like 2 to the minus n, and our body is much, much larger than the cube, but still exponentially small, right? So it's some non-trivial regime. And the proof of Gluskin, unfortunately, is completely sort of non-algorithmic. It's actually very similar to like Minkowski's theorem, for those of you know. So it uses pigeonhole principle, but it doesn't tell you anything about how to find such a point efficiently. Sorry. Okay, good. So again, yeah, this is just stating the result. So now with this powerful result, we can quickly derive what's called the partial coloring lemma. And for that, I need one very nice result to sort of lower bound the volume of a polytope. So suppose I have a symmetric polytope, which I can think of sort of obtained by intersecting some slabs. And again, by slab, I mean, some object of this type, like two hyperplanes. So Sidak's theorem says that the Gaussian measure of P is at least the product of the Gaussian measure of these slabs. And again, if these slabs were sort of orthogonal, this would be an equality. But so yeah, so what this is saying is that it's always at least as large. So if we just use this lemma and apply it to our problem where we choose these slabs corresponding to these discrepancies, we get the following result. So I can pick any lambda 1 through lambda m for my m sets. And then this theorem says that there is a partial coloring, which guarantees you that for the ith row, your discrepancy is at most lambda times the L2 norm of the ith row, provided I choose these lambda i's so that their sum is not much more than, let's say, n over 10. Right? And again, these constants don't matter really too much, right? Okay. So notice a couple of things. So one is I can choose arbitrary lambda i's, like I can treat different rows preferentially. And this statement is very powerful because I can even pick, let's say, lambda I to be 0 for omega n sets, right? Because even if lambda I is 0, this only contributes 1 to this left-hand side of this expression. So I can afford to have even a very stringent requirement that the discrepancy of these, some of these rows is exactly 0. Okay, good. So yeah, so this is the full partial coloring lemma. And again, I should say maybe, yeah, this is a very powerful result. Like almost all applications of discrepancy go via this or Banach. So let me describe a very nice algorithmic approach due to Lovett and Meka for this finding this partial coloring. Right. So again, so what Lovett and Meka showed was, right, so provided you satisfy these conditions, you can find a coloring X with omega n coordinates plus or minus 1. And the algorithm is the most natural you can think of. It's a beautiful algorithm. So the idea is, okay, you start with the all 0 coloring, right? And you start doing a random walk. So let's think of this as a Brownian motion. So you're taking very tiny increments, random increments, and you keep going and do the following two things happen. So either you hit a face of this plus 1 minus 1 cube. So some coordinate reaches plus 1 or minus 1, in which case you fix that face. So you freeze that coordinate and you keep walking in that face. Or the other thing that might happen is, you have these slab constraints, right, for the discrepancies that you don't want to violate. So maybe you hit one of these slabs, right? So AIX at most lambda I, L2 norm of AI. And then you do your random walk in this slab, right? So in this subspace, like intersected with Rn. Okay, so you'll just move in that subspace. And maybe once you move, you will hit another face or another slab and you keep walking in that, right? So by design, you won't violate your discrepancy beyond these points, which is what we wanted, right? So we just need to argue that omega n coordinates will reach plus 1 minus 1. And the analysis is very clean. So here is basically the whole idea. So let me just give it to you. So let's think of it as, suppose we take 1 over delta square steps. So again, delta is this discretization parameter of my random walk. So suppose for a moment there were no slab constraints, then basically you are just doing a random walk of size delta in each coordinate, right? So you'd expect after 1 over delta square steps that there is some constant probability a variable reaches plus or minus 1, which is great. But okay, but now you have these AI constraints which might prevent you from reaching like that, right? You might hit on these things. But the point is that, the probability that you'll hit a row AI in 1 over delta squares, so if you work out, it will exactly be e to the minus lambda s square, right? The way we have parameterized things. And the way these lambdas are chosen is that this sum is like less than n over 10. So what this basically says is that you don't expect to hit more than, let's say, n over 10 such rows as you go along. So, right, so if you keep doing this random walk, like you keep going, and every time you hit a face or a slab, you kind of lose one dimension. So maybe you get stuck when you have lost all your n dimensions, but then you can only lose n over 10 due to these slabs. So a lot of coordinates will reach plus or minus 1. And I'm being a bit informal here, but you can sort of formalize this without much work. Okay, yeah. So this gives the partial coloring. So now the point is, though, that after you are stuck, so this is kind of one phase of this partial coloring, and then you sort of have to restart the whole algorithm, right? Like sort of from the point where you got stuck, you kind of undo all the constraints and repeat. Right? So that's why it's called the partial coloring. Okay. So let me actually say one more beautiful result of Rothfuss, which was for the fully general case of this convex body. So again, so Lovett Meka only works for this case when your polytopes are given by these slabs, but it was open how to get something for completely general convex bodies, like proving Gluskin in the full sense. So here is a very beautiful algorithm by Rothfuss, and yeah, so the algorithm is just one line. So it says the following. So let's pick a random point where each coordinate is normal 0, 1. Right? So let me call this y, and just find the closest point x star in your body P intersect this +1 - 1 cube. Right? So by design, yeah, this point will lie in this cube and in the body. And the theorem he proves is that there are not, yeah, so this point will with high probability have lots of +1 - 1 coordinates. And the proof is also really beautiful. So here is the whole idea of the proof. So it relies on two observations. So first, this point y that we pick initially, it's quite far from this +1 - 1 cube, about √n distance far. And one way to see this is, I'm picking each coordinate randomly as normal 0, 1, right? So, I mean, with some constant probability, it's let's say 2 or more. So it will have ω1 distance with constant probability. So yeah, distance will be √n. On the other hand, because my body P had a large Gaussian volume, like 2 to the minus n over 100, this point y will be pretty close to P. So in the sense like √n over 100. And again, this follows from the standard sort of measure of concentration for Gaussian bodies, which, so again, probably many of you have seen this. It says, if I had a large enough body, like say volume to the minus n, then if I just add a √n ball to it, like if I grow it up by √n radius, then this almost the volume becomes close to 1. Right? So typically, if I pick a random point, it shouldn't be more than epsilon √n away. And just with these two observations, one can just prove this theorem. And the idea is, right, so when we are solving this optimization problem, we are minimizing the following, right? So we are trying to, so given this random point y, we are trying to find the x in this intersection, which minimizes the Euclidean distance. So it's a convex optimization problem. And right. And we would expect this y to be far, because it's already far from the cube. So it's definitely far from the intersection of the cube and P, right? But y is supposed to be close to P. So if this is a large distance between x star and y, so most of the non-trivial constraints must be coming from the cubes, right? Because, right? So x star must be defined by a lot of constraints of the cube, and hence a lot of coordinates must be +1 - 1. And again, sort of one can make this precise without much trouble. That's the whole proof. And after that, there were also nice results by Eldan and Singh, where you just pick a random direction, in fact, start at the origin, pick a random direction and optimize over this object, which also works. Okay, so let me quickly say, yeah, so we saw these partial coloring methods, these algorithmic methods. So one problem with them is, they only give you a partial coloring. So one typically needs log n phases to color all the elements. And because there are these log n phases, discrepancy can add up. So let's look at the Beck-Fiala example. Right. So in that example, you can show by some, I won't do this calculation, but it's not hard to show. So what you can do is the following. You can pick these lambda i's to be 0 for a set which is, let's say, large, of size bigger than t. And otherwise, lambda i's are constant. Okay. So what this means is that, I can do a partial coloring, which gets me √t discrepancy for every set. Right. So if a set was big, you'll get 0 discrepancy. And if the set is small, you'll get √t discrepancy, which is amazing. But the point is you only get a partial coloring with this √t discrepancy. So now if you do log n phases, this error can add up. Now, if you think about it a bit, you should wonder something is sort of fishy here, right? Because what I said is if a set is of size bigger than t, it has 0 discrepancy, which is great. Now, once it becomes of size t, you should think that, if I'm randomly coloring elements, a set of size t, my full discrepancy should be root t, right? Like I shouldn't lose this log n. And okay, I have like order n sets. So in the worst case, maybe I lose a root t root log n. Like there's no reason why we should lose a log n. So let's stare at why this is happening. So I claim this can actually happen in partial coloring methods. And the problem is, let's say if you look at the Lovett Meka algorithm, so recall there, as your walk goes along, you hit these slabs and then you walk in a certain subspace, right? And when you walk in a subspace, you can introduce dependencies between coordinates. So here is maybe an instructive example. So suppose you were doing a walk and you were walking in this subspace given by x1 equal to x2 equal to xt, right? And let's say you had a set in your set system of these first t elements. So now this is a problem for this set, because if you're constrained to walk in the subspace, all xi's, either they must change by plus epsilon or minus epsilon at the same time, right? Because I'm constrained. And this is really bad because, okay, so Lovett Meka ensures that in each phase you get discrepancy root t. So yeah, in one phase you won't get discrepancy root t, more than root t, but you'll only make very little progress, right? Because like progress in the coloring. So maybe here is a pictorial example on the right. So maybe this set started out big. So in the beginning, everything was great. You equally colored the elements because lambda was 0 until its size shrunk to t. But now if it shrinks to t, it could happen that it gets a root t discrepancy, but all these elements got colored blue. So, right, so yeah, you got a root t discrepancy, but you only made very little progress in the coloring. So this can actually happen again and again and again, and you can get hit. Okay, so again, sort of the punchline I want you to take is that what went wrong was that because we were walking in subspace on which we have no control, typically, you can sort of get these weird dependencies, which can really hurt you. So this also suggests then a natural idea how to get around this. And so this is where we showed with Daniel Dadouche and Shashwat Garg that how one can overcome this. So he first proved this for the Beck-Fiala problem. We got a root t root log n, and more generally root log n for Komlosh. And the idea was that, okay, we have to walk in a subspace like in Lovett Meka because you don't want to violate these discrepancies. But maybe we can design a smarter walk. So Lovett Meka algorithm was just doing a completely random walk in this subspace. But maybe we could be smarter and we can design a walk that looks random even though you are moving in this subspace. So I'll make precise what I mean by this in the next slide. But if you look at this previous example where, let's say you are constrained to walk in this subspace. So what you could do is I could set delta xi, like my increment, to be 0 for these t coordinates, right? So I'm still doing a random walk because for the other coordinates where I have no constraints, I can still do a random walk. So in that sense, I can be smarter. So even though I was forced this dependency, I kind of did not suffer from it because I'm not moving in those coordinates, right? Okay. So let me say more generally what one can do. So again, yeah, let's say there is some tight constraints W, like think of these as the slabs that we have hit, and their dimension is 1 minus delta n. And we are constrained now to walk in this W perp, right? So because we don't want to violate these things. Okay, so I claim we can use an SDP to design sort of a smarter walk instead of just doing a random walk. So let's see for a moment how we do that. So we can have two properties. So first property is just saying that your increment delta x should lie in this, should satisfy that it lies in W perp. So for every W in the subspace, it satisfies this. And if I think, okay, so I can sort of square this thing, which gives me, right? And if I define Y to be the covariance matrix of these updates, you get a constraint like this. So the point will be, yeah, we can write this as STPs. And more crucially, one can impose a constraint that your updates delta xi sort of look almost sort of pairwise independent. So what do I mean by this? So it says that if I look at any direction C, right? If I look at what's the change in that direction, so summation I ci delta xi, right? And look at the variance of this. This is at most 1 over delta the sum of individual variances. Right? So again, if these delta xi's were completely independent, this would be an equality with delta equal to 1. So it's some kind of a relaxation. And again, the point is you can encode this constraint. Yeah, so for every C, you can write this like this. And actually that boils down to just a semi-definite inequality of this type. Right? So you can sort of put both these properties that you want, like sort of really nice properties, and you can show that this SDP is always feasible. So one can define a new algorithm where at any step of your walk, you write this SDP with these constraints that I mentioned, and you use the covariance of that SDP to do your random walk. So, and the key lemma we show is that this SDP is always feasible no matter where you are. So once you do this, it kind of gets rid of this problem of dependencies that I told about. Then sort of think of intuitively as, no matter where I'm stuck in which subspace, my walk kind of looks independent because of this property. And yeah, so one can show, so again, I'll hand wave a bit, but yeah, that you don't need phases anymore, like you sort of never get stuck. And this intuition that we had that, once a set shrinks to size T, you should only incur a root T discrepancy in total, right? And indeed, one can make this precise. And yes, and so we only lose a root log n due to the union bound now. Okay. So what this does is, yeah, so this matches actually the best known bound one can get for Beck-Fiala or Komlosh more generally via Banachek's theorem. So let me in the maybe next 5-6 minutes quickly talk about Banachek's theorem and these recent ideas. Yeah,
Nikhil, we're actually running a bit short. I think you had until 1:30.
I thought it was 45, right?
Oh, sorry. Okay, no, fair enough. Sorry about that.
Okay, you also have 45, by the way. Yeah. Okay. Okay, so yeah, I'll try to wrap up in 5-6 minutes anyway, so we have time for Q&A.
No, that's great. I'm sorry, I got confused.
Yeah, right. Good. So yeah, in the next few minutes, I'll talk about Banachek's theorem, and in particular, this recent algorithm using the Gram-Schmidt walk to make this algorithmic. And this Gram-Schmidt walk, I'll just sketch a little bit because Peng will talk in much detail about this algorithm and also how to use it for experimental design. Okay, so let me state Banachek's theorem. It's a very beautiful geometric result in its own right. It says the following. So suppose you're given n vectors in m dimensions of length 1 and any convex body k in m dimensions with Gaussian measure at least a half. There is a +1 -1 coloring so that the signed sum, or like this vector balanced sum, basically lies, in maybe 5 times your body. So again, ignore these constants 5 and half. It's just some constants, right? Yeah. So morally, your signed sum lies in this convex body K. And this argument that Banachek had was sort of extremely ingenious. Unfortunately, I won't have time to talk about it. But this gives amazing results. So let's look again at our like Komlosh setting. So there, right, again, we were given unit vectors and we wanted them to have small infinity norm. So the body K that I should pick is the cube in n dimensions. And again, you need to scale this cube by root log m so that its Gaussian measure is half. Because again, if I pick a random Gaussian, like the largest coordinate is about root log m with constant probability, right? So yeah, so you pick your body K to be this, and immediately you get your Komlosh theorem, right? And again, sort of you can pick several K cleverly, and you can get lots and lots of theorems out of this. It's an amazingly powerful result. I should say one caveat. So when you first see this result, it looks very similar to Gluskin's thing. Like again, there was a Gaussian measure there, and there was some convex body whose measure had to be like 2 to the minus n over 100. But somehow there is like a crucial difference. So in Gluskin, the convex body P that we were looking at was kind of in what I call the input space, like in R to the n, right? Because our X coloring had to lie there. And in Banachek, the body we are looking at is kind of in this output space, like the sum of these sign vectors. So it's not immediately clear what's the connection, or at least I don't see it. So, but yeah, so there is this point of confusion sometimes. Good. Okay. So yeah, so how do we make this algorithmic? So there was this, yeah, so then here it's just stating the result. And the point is, right, so how do we even begin when we want to make it algorithmic? Because the way the theorem is stated, it says for any convex body K, so how is my input even given? Because to specify a general body, I might even need exponential space to begin with. So there was a very beautiful idea by Dadush, Garg, Lovett, and Nikolov, which said the following. So let's think of, so if you look at the quantifiers in Banachik's theorem, it says, for every convex body, there is some coloring X, right? So somehow this looks like a two-player game. So let's try to invert the quantification by using sort of a distribution on these X's, right? So let's apply minimax. So what this boils down to will be saying that, okay, instead of finding one coloring, you want some universal distribution on colorings, so that no matter what convex body you take with Gaussian measure half, right? Yeah, this coloring, yeah. So if you take one coloring from this distribution, it's going to work sort of with constant probability for any K. Right? So in that sense, there's a universal distribution. So it takes some work to get to this form, which I won't have time to talk about. And if you work some more, basically it gives a very clean statement. Maybe I should say a few more things. So again, it's saying, you have this universal distribution that works for every convex body K with Gaussian measure at least a half, right? So what you can do is you can actually get rid of this convex body K because it's supposed to work for every convex body. And the condition becomes a very clean condition. It says that there is some distribution on colorings X, so that if I look at this signed sum where X is coming from this distribution, this is a random vector now in n dimensions, and it's order 1 sub-Gaussian. Okay. Right. And again, by sub-Gaussian, I just mean the usual thing that, if I look at a projection of my vector in any direction, it should look like a order 1 Gaussian, right? Gaussian with variance 1. Okay. Okay, so we have reduced our problem. We have got rid of this body K, but the question has become to specify a distribution on colorings. Now that's an exponential size object, but it suffices to sort of sample one coloring X implicitly from this distribution. So that will be good enough. Right. So maybe, yeah, let me just give you some intuition how one does this. Good. So again, just recall our goal. So our goal is to find a distribution on colorings so that this is sub-Gaussian, right? And this is just rewriting the sub-Gaussianity condition. So let's look at two special cases. So suppose the VIs were orthogonal, right? So they are unit vectors, and let's say they were orthogonal. So this is a great case actually, because if you just did a random +1 -1 coloring, this would work very well because, so let's just see this, so Y, my vector that I care about, the signed sum, if I look at it in any direction theta, it's just going to be this because Y is just summation xi vi, right? And my xi's are +1 -1 random. So this is just distributed roughly as a normal with variance this, like the sum of squares of coefficients. But now the VI's are orthogonal, right? So, right. So this length by Pythagoras is at most the length squared of theta, which is at most 1. Right? Which means that, yeah, this Y is sub-Gaussian, in fact, 1 sub-Gaussian in this direction theta. So orthogonal is a beautiful case, random coloring works. But of course, random doesn't work every time. Like if your all V's were pointing in the same direction, let's say they were identical, then random coloring would be very bad, right? You could get root n variance in that direction if you did a random coloring. And indeed, in this case, ideally, we should choose things in a very dependent way, like ideally, yeah, half the guys get +1 color and other half minus V. They were identical. So this was the starting point for this Gram-Schmidt walk. So maybe I'll not define this because Peng will do this in much more detail. But the idea of this walk is that sort of we can use randomness, like in the orthogonal case, and some linear algebraic structure to kill dependencies, so that in the end, we only get one unit of variance in each direction, just like in the orthogonal case. So yeah, so it gives a very simple sort of enhanced random walk, which has this very nice property. So let me just conclude in the next minute. So yeah, so there are a lot of new recent directions in discrepancy. So one area that has seen a lot of work is in the random setting, where your set system or the matrix is coming from some random distribution. And there are very, very surprising results. Like one can do much better than the worst case settings. And Aditya will talk much more about this. One can also look at an online setting where these vectors are coming one by one over time. And when the next vector comes, you have to color it immediately without sort of knowing what's happening in the future. And in this talk, there will be a paper presented by Sahil and Makran Sinha. Okay, and there are many more applications that we'll see where there are lots of questions. So besides that, there are still big gaps in our understanding. So all these sort of classical problems in discrepancy and much more, there are still sort of these root log or worse gaps. Another direction that I find interesting is I feel there should be sort of a common generalization of Gluskin and Banashek, in the sense that if you look at Spencer's 6 root n result, so we don't know how to get it from Banashek. So even though we can do it via partial coloring, so even though Banashek looks stronger, we don't know how to do this. So there should be some right generalization. Another question that's open is, so Banashek proved a prefix version of his theorem, where given unit vectors, you can find a coloring so that every prefix is simultaneously good. And we don't know an algorithmic version of this problem. So that's completely open. So this Gram-Schmidt walk, for example, doesn't work for this. So let me stop here and thank you.
Thanks. Clap for everyone. There were a few questions. And feel free to ask more questions now before I start. So there was one question that I did not get to answer. Sorry, let me see.
Is this the one about the impact?
So
yeah.
Amit asked whether the square root log n savings that we get in some cases have an impact on applications.
So again, what depends what you mean by applications. So the square root log can be important, right? Like if you look at Caddison Singer, for instance, it was all about improving the square root log for rank 1. And even this Komlosh problem, people in convex geometry, like square root log versus constant, it's really a big thing there. So yeah, again, I don't know, like practical applications. Yeah.
Maybe I can say sometimes the question is about removing a log factor, but sometimes you get much better sort of improvements over random, I guess, if you have more structure than just a Spencer setting.
Indeed.
David Zuckerman had, maybe it's more of a comment than a question, that it's worth mentioning that pseudorandom generators may be phrased in the language of discrepancy.
Indeed, yeah. Also these epsilon nets and yeah.
Yes. Okay, that's an excellent point.
Right.
Any other questions as I'm switching? Usually you would say as I'm setting up, but I guess setting up is just clicking a button now. Okay, thank you, Nikhil.
Yeah, thanks.
Okay, hopefully everyone sees my slides. Maybe just during my talk, if Nikhil can keep an eye on questions and chat.
Yes, I'll do that.
It'd be worth opening up the participant list, etc., for the workshops. Chandra is saying me maybe worth opening up the participant list, etc., for the workshops. Okay, this is gonna test my knowledge of Zoom. I may have to look into that after my talk. Sorry about that. Hopefully people can see the questions. I think I set the settings so that everyone can see the questions that are being asked. But in terms of everyone being able to see the attendees, I can look into that after the talk. Okay. All right, so let me start. right, so I'll talk about something that Nikhil briefly mentioned, which is hereditary discrepancy, and also a connection to something called factorization norms. I'll explain both of these things. And I'll also talk about some applications in the middle. Again, hope everyone can see this. Okay, so I'll start by motivating and defining hereditary discrepancy. And then I'll talk about some applications in a little bit of detail, and then I'll end with what these factorizations norms are and how they enter the picture. All right, so let me start with a reminder, maybe not that necessary since we just saw Nikhil's talk, but good to start with a reminder of definitions, and maybe my notation is very slightly different, although it's really meant to be basically the same notation. Okay, so this is, again, a reminder of notation and definitions. So the central thing that we usually talk about in discrepancy theory is set systems or hypergraphs. The two, at least for me in this talk, are the same. So a set system is just a collection of subsets, let's say M subsets, that I write down as S1 to Sm. These are all subsets of some finite universe U. Okay, everything here will in general be finite. And the discrepancy of the set system, as Nikhil already defined it, is the minimum over all colorings of the elements of the universe with +1 and -1 as the colors of the maximum discrepancy. So you're minimizing the maximum discrepancy over all the sets. For a given coloring, the discrepancy of a set is just the absolute difference between the number of +1 elements and the number of -1 elements in the set. Okay, so the ideal situation is when every set is split as equally as possible, right? And since we chose the colors to be plus and -1, this can be nicely written as the maximum over sets of the absolute value of the sum of the colors of the elements in the set. Okay, and this can be easily extended. This definition can be extended. Very convenient to extend it to matrices. So for a matrix A, I can define the discrepancy of the matrix to be the minimum of the infinity norm of AX over where the minimum is taken over all vectors X with +1 -1 coordinates. And if I take A to be the incidence matrix of the set system, that is the matrix whose rows are the characteristic or indicator vectors of the sets in the set system, then the two definitions agree. And as Nikhil mentioned, sometimes it actually does make sense to study this matrix definition of discrepancy under other norms except L infinity, but I'll mostly stick to L infinity in this talk. Okay. So to motivate hereditary discrepancy, let me ask one, I think, interesting mathematical question about discrepancy as I just defined it, which is whether discrepancy is a robust notion. There are, of course, many ways to sort of make that formal, but let's say one thing I may want to know is whether combining, say, low discrepancy set systems in a simple way gives me another low or relatively low discrepancy set system, whether combining high discrepancy set systems in a simple way gives me a high discrepancy set system. Okay, so there are many concrete questions you can ask here. Here's one simple question you can ask, which is, if I take two set systems, let's say these are two collections of sets, which are all subsets of the same universe U, and I just take the union of these two set systems, right? So I just, I have the set systems S and T, and I just take all the sets in T and I add them to the set system S. Is discrepancy sub-additive, let's say, or maybe approximately sub-additive under taking unions like this? Okay, so is it true that the discrepancy of the union of S and T is at most, let's say, some factor, which is not too large, times the discrepancy of S plus discrepancy of T? Okay, this is false, okay? And it's not very hard to come up with examples. Here's one construction. Let's take the set system S to be sort of a bipartite kind of set system. Okay, I'm not being very precise here, but you can see why it looks like it's something that's bipartite. Okay, that's because, okay, so I'm taking the universe to be the disjoint union of two sets L and R, okay, left elements and right elements of the universe. And I'm taking the sets to be all possible ways to take T elements from L and T elements from R. Okay. Right. So it's easy to see that the set system has discrepancy 0. Why? Because I can always color the left elements with one color, the right elements with the other color. Every set has an equal number of elements from L and from R. So every set is exactly split. So the discrepancy is obviously 0. Okay, now maybe now you can see where this is going. I can take my second set system to have just two disjoint sets, the left set and the right set. Okay, the left elements and the right elements. These are disjoint, and if say they're even size, then they can both be easily split, half and half, and the discrepancy of the second set system is also 0 or 1 if you have odd size sets. But let's say the sets are even size. Okay, but now if I take the union, you immediately see that at least the coloring I have here in the picture for S does not work for T. It's very bad for T because it leaves the two sets in T monochromatic. So the discrepancy there is very large. And in general, there's a simple argument. It's just an exercise to show that the discrepancy of the union of S and T, as long as the left and right set of elements are large enough, it's easy to see that the discrepancy here is at least 2T. So basically, some set has to be monochromatic in general. Okay, so in this case, this sort of nice robustness property that we could have conjectured fails very badly. The discrepancy of the union of the two set systems is much larger than the discrepancy of the individual set systems, which is 0. Okay. Good. So this motivates defining a more robust notion of discrepancy. And one way of doing this was proposed by Lovett, Spencer, Westergombe back in '86, who introduced the notion of hereditary discrepancy. So to define that, I need to introduce a simple definition. The simple definition is the definition of a restriction of a set system. Okay, so if I have a subset W of the universe, then the restriction of the set system S to W is just the set system I get by intersecting every set in S with W. Okay, so I just throw away everything in the universe that's not in W. I throw those elements away from every set. Okay, very natural notion. And now the hereditary discrepancy is simply defined as the maximum discrepancy over all restrictions of the set system. Okay, and again, it's easy to extend this to matrices. So the hereditary discrepancy of a matrix is just the maximum discrepancy over submatrices of the given matrix, which I'm calling A. You just maximize the discrepancy over submatrices. And again, if you take A to be the incidence matrix of a set system, the two definitions agree. Okay, so this is hereditary discrepancy. Is it actually something that's more robust? First, I'm going to let's first just check what happens for the example we had where the discrepancy of the union is much larger than the discrepancy of the original set system. I'm claiming this is not true anymore for this example, at least, for hereditary discrepancy. Why? The reason is that if you take the first set system, again, this is a set system where I have left elements and right elements, and the sets are all possible ways to take T elements from the left and T elements from the right. I'm claiming now the hereditary discrepancy here is very far from 0. It's actually on the order of T. Okay, so one way to see that is, in particular, hereditary discrepancy, by definition, is at least as large as the discrepancy of any restriction, right? Because it's the maximum discrepancy of all restrictions of the set system. So let's look at, let's say, the restriction to the right elements. Of course, I could also do it for the left elements. Everything is completely symmetric. Okay, and of course, the restriction of the set system to the right elements is just the collection of all possible subsets of size T of the right elements. And if the number of right elements is large enough, then it's easy to see that the discrepancy will be at least T. Basically, there would have to be some monochromatic set here. Okay, therefore, the hereditary discrepancy is also at least T. So at least you can see, okay, it's no longer going to be true that the hereditary discrepancy is going to, of the union is going to jump up from 0 to something on the order of T. It's not hard to convince yourself that for this particular example, the hereditary discrepancy of the union is at most a constant factor larger than the sum of the hereditary discrepancies of the two individual set systems. Okay. And in general, okay, so this is not something that's just true for this example. This is a general phenomenon. Hereditary discrepancy satisfies a lot of nice robustness properties that are, so it sort of behaves nicely under taking unions and a lot of other natural operations, either on matrices or on set systems. Okay, so let me give a few examples. Let me, for the next few points on this slide, S and T be two set systems, let's say with M sets, which are, let's say, set systems on some common universe U. Okay. And in particular, the hereditary discrepancy of the union is at most, in all cases, at most a polylog factor, polylog in M factor times the sum of the hereditary discrepancies. And in fact, you can do a little bit better. You can say that the hereditary discrepancy of the union is at most a polylog factor times the square root of the sum of the hereditary discrepancy, the sum of the squared hereditary discrepancies. There is a natural notion of a dual of a set system, which basically swaps the roles of sets and elements of the universe. And it turns out that the hereditary discrepancy of the dual set system is at most a polylog factor times the hereditary discrepancy of the original set system. There's also a natural notion of taking products of set systems, where the product of the set systems S and T is defined as the set of all cross products of individual sets in S with individual sets in T. Okay, so all ordered pairs of elements from Si and Tk, where Si is in S and Tk is in T. Okay, and the hereditary discrepancy is sort of approximately multiplicative under taking products. So the hereditary discrepancy of the product of S and T is at most a polylog factor times the hereditary discrepancy of S times this discrepancy of T. And this inequality also holds in the other direction, where you put the polylog on the other side. Okay. So up to polylog factors, the hereditary discrepancy of the product is the product of the hereditary discrepancies. Okay, and in general, for all of these, the polylog factors, some polylog factors are in general necessary. What power of log could be open in some cases. Okay. And all of these fail for just plain discrepancy if you don't have hereditary here. Okay. Right, so we'll see a little bit more about these things, about why these things are true a little bit later in this talk. Okay, so I've said a bit about hereditary discrepancy. I've mentioned why. Let me answer a question live now. So Kartik is asking if these relations also hold for other norms instead of the infinity norm. That is a good question. And right. Okay. So yes, that's an excellent question. Yeah, I think in general, if you measure discrepancy with other norms, these sorts of properties do not have to hold. Some of them do, but you have to be a little bit more. You have to be a little bit more careful. Things like union of set systems, or putting, which is kind of equivalent to putting matrices one below the other, behave very nicely with L infinity. May not behave so nicely with other norms. But I think in general, you can at least say that there is sort of an approximate kind of a triangle inequality for discrepancy under other norms that you can prove. I think I'll leave it at that at this point. What is the intuition? And I have another question, which is, what is the intuition for the polylog M factor for all cases in hereditary discrepancy? So yeah, again, it would be a little hard to say without looking at concrete examples. But let me say, for example, you can come up with examples where you can take the union of two set systems. Both set systems have hereditary discrepancy 1, but the hereditary discrepancy of the union can be as high as a log factor. So one example is discrepancy of set systems given by permutations. So the sets are So you have some fixed number of permutations, say 1, 2, or 3, and the sets are all, say, intervals in these permutations. So the hereditary discrepancy is 1 for 1 or 2 permutations, but is log of the number of elements for 3 permutations. And of course, you can make the set system for 3 permutations out of taking the union of a set system on 1 and a set system on 2 permutations. So this is one example where you see this kind of behavior, at least for unions. Okay, thanks. I guess it's not that hard to monitor for questions. All right, so let me now also talk a bit about applications. So far, I've argued that hereditary discrepancy has some nice robustness properties, and this also makes it quite useful for applications. Basically, if you have a more robust notion, it's more easy to apply it because it allows usually some sort of recursive argument. So let's see some examples, and this would make more sense. So the first application is also due to Lovett Spencer Westergombe, and this is something that Nikhil alluded to in his talk, and is the following rounding result. So it says that for any matrix A and any vector W with real entries with like real coordinates between 0 and 1, there exists a rounding of W, which is a vector X with coordinates that are either 0 or 1, okay, such that the error when you do this rounding with respect to A is at most hereditary discrepancy. What I mean by that is that the infinity norm of the difference between AX and AW is at most a hereditary discrepancy of A. Okay, I won't really try to give a proof. I'll give sort of hints if you want to do the proof at home as an exercise. First step is to prove this when W is half integral. So every entry is 0, half, or 1. Then it's really easy to show this even with a factor half in front of hereditary discrepancy. So you can even do a little bit better. And now you want to apply this exercise, the result of this exercise, to the bits of W when you write W in binary. Let's say you can assume that W has rational coordinates by some approximation argument. Okay, and yeah, that's the hint for the proof. I'm not going to give the full proof here. You can find it in the book by Matuszek, for example, or in the book by Chazelle. Again, this result can be quite useful for approximation algorithms, although it would be nice to get more examples of applications. But there's some already quite nice examples of applying this result to approximation algorithms. For example, the best currently known algorithms for approximating the bin packing problem due to Kohlberg and Rothfuss, building on prior work by Rothfuss, use this type of result with other ingredients. And the general idea is that you can write many NP-hard optimization problems as an integer program, which you can relax to a linear program. Then you can solve the linear program to get this vector W. And then you can apply the theorem to round this W to an integral X. Because you get sort of errors when you do this rounding, this X will be only approximately feasible, but sort of how far it is from feasible is controlled by the hereditary discrepancy. And then the idea is to fix the validated constraints in a way that doesn't hurt your objective too much. And that's going to be problem specific, but it can be done in the bin packing case, for example, and you can sort of quantify how much fixing these constraint violations hurts your objective function. And Chandra is asking if it would be helpful to indicate some set system with small hereditary discrepancy. Yes, we'll see another example. And unfortunately, I kept it towards the end. I should have given an example early on. But let me say probably the simplest set system with, okay, so, probably the simplest set system with really small hereditary discrepancy, which is hereditary discrepancy 1, which is as small as it can get, is a set system where the elements are the integers 1 through n, and the sets are all intervals on these integers, let's say from 5 to 300, right? From square root of n to 3 square root of n. So all sets like this. This has hereditary discrepancy 1, which is pretty easy to see because you can, for any restriction, you get the same type of set system, and you can always color the elements +1, -1 in an automatic manner. And then, as I mentioned, you can now take a few different permutations of the integers 1 through n and take all intervals according to each permutation. And those set systems also have relatively low hereditary discrepancy. So maybe that's useful to keep in mind. Okay. Sorry, I think someone is... Nikhil, I'm going to mute you. Okay. All right. So this is one application. Let me mention another application, which will be sort of a reason to mention maybe other types of set systems with small hereditary discrepancy. So this was also alluded to by Nikhil. In this application, we're looking for well-distributed sets of points. And I should say this is also related to pseudo-randomness. But let me present this in a more geometric setting. So let's say we have S2, which is some family of geometric sets in D-dimensional Euclidean space. For example, we can take the family BD, that's what I'm calling the set of all axis-aligned boxes in D dimensions. So for example, in 2 dimensions, this would be all rectangles with horizontal and vertical sides. Okay, and now let's say we also given some probability measure on D-dimensional space, which I'm calling mu. And the goal is to find a set P of endpoints so that the uniform distribution on P is as close as possible to mu with respect to the sets in S. Okay, so we want the uniform distribution on P to, in some sense, fool all the sets in S. Okay, so in this case, the continuous, what I'm calling the continuous discrepancy, to distinguish it from the discrepancy we've been talking about, is the following. It's the maximum over all sets S in S of the fraction of points of P that land in S minus the measure of S under mu in absolute value. Okay, so this is the maximum difference between the measure assigned by the uniform probability on P to S and the actual measure assigned by mu. Okay, so this is a sort of a natural way to measure how well does the uniform distribution on P fool the sets S with respect to whether we have that distribution or mu itself. Okay, and the goal is to minimize this over all sets P of endpoints, sort of overall sparse uniform distributions. And an interesting connection here is the so-called transference theorem that says that under some mild technical conditions that I'm going to skip, for any family S, there is a set P of endpoints, so that the continuous discrepancy of P is at most 1 over n times the maximum possible discrepancy of S restricted to some finite set of endpoints. Okay, so the right-hand side here, if you ignore the 1 over n, this maximum overall discrepancies of restrictions to endpoints, this is not quite hereditary discrepancy, but it's sort of an analog of that. So I would still call this an application of hereditary discrepancy. And Nikhil sort of briefly indicated the proof in his talk, so I'm going to skip it here. Okay, and finally, I want to mention one last application, which has a bit of a different flavor, maybe is a bit less known. This is an application of hereditary discrepancy to differential privacy. So this is also relatively much more recent, but it leads to some surprisingly clean results. Okay, so let me give sort of a 1,000 feet overview of what is differential privacy. I will skip a lot of important details. Okay, so the setting here is that I want to answer statistical questions about a set of people without revealing who those people are, roughly speaking. Okay, so the setting is that we have some data set X, capital X, which is drawn from some population U, and we want to answer questions about this set X. So think of this data set X as people participating in some survey, for example. And there are many different, statistical questions now you can ask about this data set. Basically, anything in statistics or machine learning is fair game. I'll talk about the simplest possible question you can ask about X, which are what we call counting queries. Okay, so counting queries are conveniently for this talk given by basically set systems. So there is one query we make to X given by each set SI in a set system S. That query is basically asking how many points, how many data points in X lie in SI. For example, we can have some set system where S1 is the set of all points representing female smokers in the population. S2 is the set of all, say, male PhDs who are not smokers, and so on. And then the first counting query would ask how many people in the data set are female and smoke. Question 2 would ask how many people in the data set are male, do not smoke, and have a PhD, and so on. And these kind of questions are very simple, but they capture many sort of statistics that are released about people, including statistics released by things like census bureaus. Okay, and a basic question in differential privacy and in private data analysis more generally is if we can approximate these kind of counting queries without revealing who is in the dataset X. And this is motivated by privacy concerns. And let me kind of define differential privacy without really giving the actual definition, but giving enough of an idea to give you sort of a hint of what this is about. So differential privacy, this is a definition due to Dwork, McSherry, Nissim, and Schmidt. And it says that a randomized algorithm A is differentially private if, again, this is a randomized algorithm. So the condition is that the distribution on outputs of A when the input is X and the distribution on outputs of A when the input is X prime should be close. When X and X prime are two data sets that differ in the data of at most one individual. Okay, so the algorithm should do almost the same when you give it data sets that differ in only one person's data. Okay, and what it means for the distributions to be close here is something I'm not going to define. Of course, you need to define that to get the actual definition. And there are a few different ways to do that, which give slightly different versions of differential privacy. Okay. So what can we ask about, sort of what scientific questions can we ask here? Let me start with a basic fact that predates and motivates a lot of differential privacy. This is a result due to Dinur and Nissim from 2003, which quantitatively at least says that an algorithm that answers sufficiently many random counting queries with sufficiently high accuracy, sufficiently low error, would allow you to reconstruct almost all of the data set X. They called this situation blatant non-privacy because you don't just violate someone's privacy, you even violate most people's privacy, most people in that data set. And this in particular violates differential privacy, but it really violates almost any sensible notion of privacy, I would say. So this fact sort of tells us that when we want to answer counting queries, when we want to sort of answer these kinds of counting questions about data while preserving privacy, we will have to deal with error. We'll have to deal with approximations. And you can ask, what is the minimum error that's necessary to answer a set of counting queries given by some set system under differential privacy? For example, what is the minimum expected maximum error that the algorithm makes over this set of counting queries, where we minimize this over all possible differentially private algorithms? Okay. And it turns out that this question has a relatively clean answer, at least up to polylogarithmic factors. This optimal achievable error for the set of counting queries given by its S system S is given up to polylog factors by the hereditary discrepancy of S. Okay, so we have both an upper and a lower bound on the optimal error. That's in terms of hereditary discrepancy of S. This is a result due to myself, Tawar, and Zhang from 2013. Okay. And let me give some idea of where the lower bound on error comes from. And this comes, again, from a reconstruction result, which is something we showed with Muthukrishnan in 2012. We showed that for any set system, there's some restriction of the universe. There's some subset W of the population of the universe, such that if you draw a data set X from that subset W, then for any such data set drawn from W, if I give you answers to the queries given by the set system, where the answers have error much less than the hereditary discrepancy of the set system, say hereditary discrepancy over log m, then this would allow reconstructing, in general, most points of x. So all points of x, except maybe 3/4 of the size of W. And the idea here is, okay, so let's say I have some set W and I draw data sets from this set W. What if, let's think what would happen if this was not possible, if I wasn't able to identify X from the query answers. This would mean that there exist two data sets, X and X prime, that differ in more than 3/4, whose symmetric difference is size more than 3/4 the size of W, that differ in a lot of points, but give approximately the same answers to all the queries. Let's say up to a plus minus D, where D is some parameter. Okay, and I'm claiming if that's the case, then there exists a good partial coloring of W with discrepancy 2D. And the partial coloring is just given by the difference between the indicator vectors of X and X prime. Okay, and you can easily verify that the discrepancy here is 2D and that this coloring colors most elements of W. Okay, so if it was true that for every W we cannot reconstruct, then we would have a partial coloring. If you have a partial coloring for every W with discrepancy 2D, then it's easy to sort of combine the partial colorings recursively and get that the hereditary discrepancy also is at most log m or a log m factor times D. Okay. Maybe I can actually answer this question. So given a set of random matrices, is there anything known about the probability distribution of the corresponding discrepancies of this set? So we do know that for random 0, 1 matrices, the discrepancy, at least in some parameter regimes, is basically on the order of the discrepancy you can get from a partial coloring, at least if you have enough rows compared to the number of columns. And I believe Aditya in the final talk will talk more about discrepancies of random matrices. And there's another question. Does this result imply that we need to restrict the set of possible queries in some way to ensure accurate differential private algorithms? Yes, in particular, it does. This result does, I guess, say that if the queries are given by a high discrepancy set system, then you cannot guarantee at least differential privacy without a lot of error. Okay. All right, so this basically says that if the discrepancy is high, then even with a lot of error, you can get these reconstruction attacks, which in particular contradict differential privacy. So this gives the lower bound part of this connection between hereditary discrepancy and differential privacy. This gives the lower bound on error. The upper bound, I won't say so much about, but I'll mention a little bit about it in a little bit. Okay, so in the final part of the talk, in the next few minutes, let me say a little bit about proving some basic bounds on discrepancy and what is this connection to these factorization norms, which I also have not defined yet. Okay, so what I want to mainly focus on is how do you prove upper bounds on hereditary discrepancy? Remember, hereditary discrepancy is a maximum over every of the discrepancy of every restriction of the set system, or equivalently the maximum over the discrepancy of every submatrix. So proving upper bounds on hereditary discrepancy is not obvious because it's a maximum over an exponential number of quantities, where each quantity itself is actually quite computationally difficult to understand. Okay, so let me give you an idea how you can prove some simple upper bounds on hereditary discrepancy, nevertheless. Okay, so let me introduce some matrix norms. Okay, so there's a question which I think I'll return to later. Let me introduce some matrix norms now, which will be useful. So, sorry if the notation is not very intuitive. It's standard, and there's a reason why it's like that. Hopefully, it's not too confusing. So, I need two norms for now. For a matrix A, the 1 to 2 norm of the matrix is the maximum L2 norm of any column of A. And the 2 to infinity norm is the maximum L2 norm of any row of A. Okay, and I'm claiming that hereditary discrepancy is first at most a root log m factor times the maximum L2 norm of any row. That is the 2 to infinity norm. Okay, why is that? Let's first argue that the discrepancy is at most this much. And that's just because you can take a random coloring and you can apply something like Hofding's bound and a union bound to get this result. Okay, so this is just achieved by random coloring. Okay, this is an upper bound on the discrepancy of the full matrix. But now for any submatrix, the maximum L2 norm of any row can only decrease when you go from a matrix to a submatrix. So that is the 2 to infinity norm can only decrease when you go to submatrices. So this upper bound automatically holds for submatrices as well. And therefore, it's also a bound on the hereditary discrepancy. And the same logic, but with some more work, applies to the 1 to 2 norm. There, the bound on discrepancy itself follows from the best known bounds for the Komlush problem, which is something that we saw in Nikhil's talk. And again, the 1 to 2 norm is monotone down, so it only can decrease when you go to submatrices. So the bound on discrepancy automatically holds for hereditary discrepancy as well. Okay, so both these bounds can be useful in some cases, but also neither of them is generally tight. For both these bounds, you can come up with examples where the upper bound is very far from a lower bound. Okay, or in other words, it's very far from truth. Right, so how do we get sort of the true bound? How do we get a tight bound? And you can get a tight bound by sort of combining these two upper bounds. Okay, so we need one more matrix norm. This is what we call a factorization norm. So this is the gamma 2 norm of the matrix A. And it's equal to the minimum of the product of the 2 to infinity norm of a matrix B times the 1 to 2 norm of a matrix C, where you take the minimum over all matrices B and C, whose product is A. Okay, so I take the minimum of the maximum row norm of B times the maximum column norm of C over all matrices B and C, whose product is A. And we have a result, which was first proved in a paper of mine with Untitled and was refined a little bit in a subsequent paper with Matuszek, where we showed that for any matrix A, the hereditary discrepancy is sandwiched between square root of log m times the gamma 2 norm and the gamma 2 norm divided by log m. This is up to constant factors. Okay, so I'm ignoring constant factors here in the notation. And in general, neither bound can be improved. So both bounds are tight for some matrix A. Obviously not at the same time, right? So for each of these two bounds, there's a matrix A for which the bound is tight. However, and I won't say much about this, but there is a more recent work with Daniel Dedush, Kunal War, and Nicole Tomczyk-Jagerman, where we show that a different factorization norm gives a similar result, but the factors are not log in M, they're polylog in the rank of A, which can be useful in some cases. In particular, it implies results also for discrepancy under other norms. Okay, so why is this useful? I have just argued that there are these two notions, the gamma 2 norm and hereditary discrepancy, which are all approximately equal, but so what? And the reason this is useful is that the gamma 2 norm is very nice in general. It has a lot of very nice properties. In particular, it's a norm, which is not an entirely obvious fact, by the way. But it is a norm. It satisfies the triangle inequality. It satisfies a slight strengthening of the triangle inequality if you look at two matrices that you stack one on top of the other. It's invariant under taking transposes. This is very easy to see. And it's multiplicative if you take the chronic or tensor product of two matrices. Also, the gamma 2 norm can be computed in polynomial time. So all these things are also approximately true now for hereditary discrepancy because the gamma 2 norm is approximately equal to hereditary discrepancy. In particular, we also have an approximation algorithm for hereditary discrepancy out of this connection. And there is also a differentially private algorithm for counting queries whose error is bounded in terms of the gamma 2 norm, which gives also the other side of this connection to differential privacy. And this has been improved and refined in a paper in this conference, which was presented this morning by Alex Edmonds. This is also with John Ullman. Okay. Let me finish briefly with one more example of a set system with low discrepancy. So recall that I used BD for the set of axis line boxes in D dimensions, for example, sort of axis line rectangles in 2 dimensions. And a long-standing question here is to understand the maximum discrepancy of set systems induced by axis line boxes restricted to point sets of n points. Okay, this is what I'm calling this function delta D of n, the maximum discrepancy of such a set system given by axis line boxes restricted to n points. Okay, so let me sketch a brief argument for sort of trying to understand the growth rate of this quantity. So first, it's not very hard to argue that without loss of generality, you can assume that the point set P is a subset of the n like n by n by n and so forth d times grid. So the grid with n points in each sort of row and column. So therefore, this delta D of n quantity is approximately the hereditary discrepancy of the set system induced by axis line boxes on the grid. And now it's not hard to see that the incidence matrix of the set system is just a tensor power of the incidence matrix of the corresponding one-dimensional set system. And then hereditary discrepancy of this set system is, as we saw, approximately equal up to log factors to the gamma 2 norm of this tensor power of the incidence matrix of the one-dimensional set system. But the gamma 2 norm is multiplicative under tensor products. So this is equal now to the gamma 2 norm of the one-dimensional set system to the power d. And it's easy to analyze the gamma 2 norm of the one-dimensional set system, or the corresponding incidence matrix, and that's on the order of log n. So we get that the gamma 2 norm here is on the order of log n to the d. Okay, and again, this is approximately equal to the hereditary discrepancy. So if you work things out, you get that this maximum discrepancy of rectangles is between log n to the d plus half and log n to the d minus 1. So this almost gives you the order of growth of the discrepancy of d-dimensional boxes. And the upper bound can be proved by another log factor with a more careful argument, which was done in a paper of mine from about 3 years ago. Okay, so this is another illustration of how the gamma 2 norm can be very useful here, and its properties can be very useful. And I'm going to stop here. Here's some open problems. We just mentioned 2 of them. One is completely resolving Tushnadi's problem, so determining the discrepancy of boxes. And another sort of interesting bit here is that the current best upper bound is not really algorithmic, even with all the tools given by Nikhil. And another question is to determine, for example, the best possible approximation factor for hereditary discrepancy. It's somewhere between 2 and a log, or a power of log. We don't know where exactly. All right, let me stop here, check the questions. Chandra said random queries have essentially communication complexity that depends on the data set size. Is there work on quantifying discrepancy, hereditary discrepancy based on descriptive aspects of the queries? That sounds like an interesting direction. I'm not aware of anything in that direction. Definitely worth thinking about. Thanks, Chandra. Karthik said, can you briefly say how to compute the gamma 2 norm? Can I? Let me see. So one nice thing here is that the gamma 2 norm can be written as the value of a semi-definite program. And then you can both give basically a factorization to certify an upper bound, and you can give a dual solution to certify a lower bound. So you can do it with analyzing the eigenvalues of some particular matrix. And maybe I can give, okay. Karthik also asked, follow-up question, can I show the definition? Here's the definition of the gamma 2 norm. So to give an upper bound on gamma 2 norm, you can basically give the matrices B and C. To give a lower bound, you can find basically a dual formulation of gamma 2 norm. and give a dual certificate of a lower bound. Amit asked, is there a useful bound on large dimension? Maybe how large the dimensions of B and C need to be in the definition of gamma 2? Yes, so the outer dimensions should be the same as the corresponding dimension in A, and the inner dimension is, I think, always at most the minimum of the outer dimensions, maybe even the rank. Okay. Any other questions? And I'll stop sharing. And I'll let, I'm sorry, who is next actually?
I am. Zohar.
Is it Zohar? Okay. Zohar,
Yeah.
you can share your screen. I'll stop my video.
See. See me struggling.
So it's your video, but not the. Not the slides yet. Ah, there you go.
See if it. Okay, can you see the slides now?
Yes.
Perfect.
Okay, so we have Zohar Karnian, who's going to tell us about another application of discrepancy, this time to constructing course sets and sketches in machine learning. And feel free to take it away.
I'll move mine. All right. Thank you. So I'll jump to it to start by defining what a course set is. So the idea is, imagine, we have a function that can be decomposed into many small ones. So this is kind of a k-means motivated example where I get queries labeled by Q here, and I want to compute the value of some f of Q, which can be decomposed into a sum over items xi. So the sum is over I of some function f of xi and q. This could be like a Euclidean distance or some simple function usually. And it's very common that I'll have a lot of these instances xi, and I'll need to either store all of them in memory or answer a lot of queries for this queue. And when this happens, I may agree to get an approximate function, this f tilde here, that is not exactly equal to what I wanted, but it's going to use only a very small set, a small sample of these original items, right? And possibly they'll have different weights. So, in this case, this point represents a lot of points, and this one represents only one or a few, right? And these two functions, the original capital F and the approximation, should be close in, I guess, infinity norm, meaning for every query Q, wherever it may be, these answers should be the same. And the query Q could be the same, the same item, such as these X points. And, it could be basically anything. Like in this case, the X's are points in a two-dimensional space, and Q is a point or a vector. Right. And here again, the objective is, how can I find this small representative subset? Right. And, first attempt, just subsample. Right. I mean, that's going to work. It gives you guarantees. Sometimes it's also very hard to beat. But just like the case of discrepancy, the question comes, can we do better? And, this definition should not be very surprising by now. A very similar question is function-based discrepancy. It's really the same definition. Instead of matrices, you can think of a matrix for all possible q's or something like that. But really, imagine, this f function is a sum over the small functions f, and now I get to insert these signs, sigma I, and I get to choose to define them in any way I want. But what I really would want to have is to make this negated sum to be as close to 0 as possible for all possible queries. And this would be the class discrepancy of this function f. And discrepancy tool will help me achieve this. And apparently, there's a pretty easy way to go from a discrepancy result to a corset result. The corset is, instead of having all the points with equal weights, I get a subset of points, possibly unequal weights. And this is the additive form. I won't talk about multiplicative form, which is where the accuracy has to depend on the value of q. The additive has enough applications. So, you can move from one to the other, and to show how, I figure I'll go with a very simple example of approximating a CDF or quantiles of a distribution. So the function here I care about is the simple step function. If q is larger than x, then it's 1, otherwise it's 0. And if I see a lot of numbers coming from a distribution, I'd like to know what this distribution is. Is it, is it Gaussian or Zipfian or something like that? I can store all these numbers, then I sort them, and I have my approximate CDF, which is just the sum of all these step functions, right? And if I see too many of these, I still want a good approximation, and I don't want to keep all the numbers. So really, I want, an approximate CDF, this f tilde, which is close enough in the infinity norm, meaning for every query q, I want it to be, the approximate rank should be close to the rank. And this is a very easy exercise. You can set up the signs so that for any possible query q, this sum of signed step functions is no more than 1, right? Just sort the values and give them, +1, -1, and so on. And why does this help me? Well, if I just take the negative signed vectors, I get this red f tilde, and it's a corset whose size is half the original, and error is at most 1, right? And I guess that's a different way of viewing it, but you probably got the point. And so I got from n points to n over 2 points, and I can do it again to n over 4 and so on. And if I do this log times, I would get a corset of 1 over epsilon, whose error is epsilon. And this happens to be the best thing you could do for approximating a CDF. Right, so really, this example just generalizes to any function, right? We saw for this function, for the step function, the bound for the discrepancy is 1, and we obtained a corset of size 1 over epsilon. And it generalizes even more than this, but I guess the interesting part, in many interesting cases, the class discrepancy is some constant over M. I guess O can have the constant, something that's independent of M, the number of points, is the class discrepancy. And this would mean that we get a corset whose size is 1 over epsilon, or C over epsilon. And so far, this is a easy exercise, but it gets a bit, I guess, more interesting when you have to do it in a streaming setting. So in a streaming setting, you don't get to take multiple passes over your data, but you see the items one by one and need to decide what to do with it. Is it in the core set? And I guess an early work to do this is the known merge and reduce. I guess you could call it a trick. And the idea is the following. So this bottom line here is the original stream, and I'm going to collect it. I have a buffer that sees the items and collects 2 k items. K is some parameter. And once it saw 2 k items, it'll use, the discrepancy bound to get a set of size k, which is half, and it'll push them to the next stream that has items of weight 2. And so from n items of weight 1, I got n over 2 items of weight 2, and this is in a streaming setting, so I had to use k slots or 2k slots. And I do this again in parallel, and again, and eventually I have log n buffers that have to run and process this stream. And each of these buffers get, collect items until it reaches the capacity. Then it pushes only half of what it had to the next buffer. And you end up having, log of n times the buffers, and you get a memory bound. And this was done for this example I'm running with approximate CDF or streaming quantiles by MRL a while back. And it generalizes to really any function type. So if the class discrepancy is some constant independent of the number of points over m, then in a streaming setting, you have to pay this log square factor. And why square? Because you have log many buffers and the error accumulates, so everyone has to have an error of epsilon over log n. So it's log square. And this is deterministic. And if you're willing to have a randomized version of this, you can actually get a little better. And again, I'll use the quantile example. So here, we have a buffer that got full with 6 numbers in this case. I color them according to my discrepancy algorithm. And before we said, it doesn't really matter which one you output, either the positives or the negatives. And indeed, no matter what you do, your error is bounded by 1. But if you choose one of them at random, the error is not only bounded by 1, but it has an expected value of 0. And so you can keep tabs of this error, and it's a sum of random signs. And again, in this view of buffers that the first one sees n item, the second one sees half n over 2 items, n over 4, then I have 2 ways of bounding the error. So this error, I can have this is an expression that details the error from moving to stream of n to n over 2, or from n over 2 to n over 4. So the overall error is the sum of these, this h. And I have 2 bounds. The discrepancy is what we used before. Just give me an absolute bound of, if I use a buffer size k, I'll need to make these these operations of compacting n over k times, and that's going to be the bound. But the other one, from a sum of random directions, it lets me get a Chernoff bound that essentially does something like this. So here, I need a union bound. So Q, capital Q, is the collection of all the possible queries. It could be infinite, but then we use an epsilon net, right? And the second bound, it could actually be better. If my stream length is very large, then this looks like square root of n, and this one is linear n. So really, you end up having this type of analysis. For the lower levels, you actually want to use the statistical bound. And for the upper ones, you want to use the deterministic bound. And this was, well, very implicitly done in a paper, again, for streaming quantiles. Felber and Ostrovsky. And another improvement, notices that if you look at this bound here, you see that here you have a lot of small signs, and here you have less signs that are bigger, and so on. So the error at level 3 is larger than the error at level 2. So you might as well invest less resources in the lower levels. So what you can do is just have a exponential decay in the resources you invest, and you end up using less memory and getting the same error bounds. And this was yet another paper on, well, quantiles. But again, although all these were done for streaming quantiles, it actually generalizes to, well, any core set if you have this discrepancy bound. And just for the analysis, here this line comes when the size of the stream is roughly log of Q. So you end up having log of Q layers, and this gives you the bound that replaces log of n, which grows as your stream grows to something that is independent of n, which is log of some epsilon net. So this could be exponential, but still, this is a double log. So this is a meaningful bound. This was in a Cold paper last year. And now so that was for our core sets, and it's on to machine learning and core sets. So just a general, an interesting problem in machine learning is the issue of generalization. So you have a infinite possible or very large pool of data points, which are these xi's. And the common setting everyone assumes is happening is you sampled a bunch of IID data points from this pool, maybe according to some probability distribution, and now you're solving the empirical risk, it's called. So you're just solving, this is your loss function for a possible machine learning model. So here Q is a machine learning model, say a linear function, and this could be the squared loss. But really Q could be anything, right? It could be some deep network or any kind of model, and this could be the loss of that model. And the question comes, let's say I solve this, how well does this generalize? Because I don't really care about the performance on my sample. I care about the performance on new points that I haven't seen. So really I care about this quantity. For points coming from this distribution, what is my loss? And a common tool to do this is what's called the Rademacher complexity that, well, gives this quantity. So what you do is you take these m points and this function f that determined the loss, you put in random signs in front of it. And then you measure for the worst possible model Q, how far away is this thing from 0? And this would be the Rademacher complexity. And as it turns out, I'm sweeping a lot of stuff under the rug here, but your actual loss on data points coming from the distribution is bounded by the the actual loss of what you found is bound by the best possible loss you could hope for, plus this complexity measure, right? And now comes a less standard setting. So instead of selecting these points in parallel, let's just carefully select them. So I'll just lay out a lot of points, and somehow I'll choose m points, not at random, but in some clever way. And I'll do the same thing, the same solver for my machine learning problem. I'll just apply it. And now I ask, how well does this do? And apparently it behaves in a very similar way, just instead of having this Rademacher complexity where sigma is random, you get to choose the signs yourself. So if this quantity happens to be lower, then you're in luck because you got better generalization bounds. And I guess now comes the question. I mean, okay, it's different formulation, but is it really different? And the answer is, well, it says no, but I asked the inverse question, so the answer is yes, right? So Rademacher complexity would usually be something divided by square root of m. And coarset complexity, of course, it's sometimes unknown, sometimes it's maybe not this, but it happens that in many interesting cases, it actually is a constant divided by m. So this means that if you handpick your data points, you can actually solve the problem on a much smaller set and get away with, choosing less points to train on, and you get much better, generalization bounds. It scales, inversely linear in M and not inversely linear with the square root of M. And yes, some concrete examples for functions that, this was very abstract, these f functions. So here's two explicit functions, log of 1 plus x of xi times q, and the e to the minus square distance. So for these one-dimensional functions, I won't show for them, but it actually is, the complexity actually is some constant over m. And if you look at the vector form of these, so instead of product between numbers, now xi is a vector and q is a vector, and I took the inner product, and here I took the Euclidean distance. And as it turns out, so first, before I talk about the complexity, this is logistic regression. So in logistic regression, you take these functions, you sum them and for q, and you minimize, you find the linear function q that minimizes this logistic loss. And this is Gaussian kernel density, where you have a bunch of points, and the density of a query q is the sum over this function. This is used for classification. This is used for detecting outliers. So often enough, it works pretty well that you have a collection of points, say for fraud detection. You want to see if a new data point looks weird or not. And so you will compute this density, and if it's very close to 0, then it looks weird. It's really far away from anything you've ever seen. So you promote this as some kind of inspection. And as it turns out, yes, this thing is some constant over m. I'm not sure I have the time for the full proof, but really what you can show is that for functions of inner products, you can actually get a discrepancy bound by looking at the Taylor expansion. So if you look at the Taylor expansion of this thing, this sine times f, this is just the Taylor expansion, then an inner product to the power of k is an inner product of tensors. Take the Kronecker product. Then everything is linear, so we can move the coefficients around. And then you end up having to bound an operator norm of a tensor. And you can do that. I guess for vectors, it's a bit easier to vector. It's one-dimensional tensor. It's, if you take random signs, you'll get a random walk, and this would get you something with a square root n norm. But if you get to choose the signs, you can actually get this down to square root of d. And I'll skip the questionnaire, but for a matrices, two-dimensional tensors, spoiler, it's also square root of d, but you need to multiply it by 2. And the way you prove it is with Banaszczyk's theorem. that, you know, I guess I have 2 minutes left, so I won't get into it. And I think we saw this about an hour ago. So really, you look at Banachik's theorem helps you. Well, it's not constructive, but it tells you that you can balance vectors from a convex set. And in this setting, the convex set is the set of matrices with bounded operator norm. So basically, it just tells you that you can balance the norms, and if you play with, figure out all the constants and dependencies, you'll find that it's bounded by a constant times square root of d. And for k-dimensional tensors, it's square root of d times some polynomial of k, of the dimension of the tensor. And so if you plug this in, you end up having this bound, and as long as, and this is the Taylor expansion, right? So as long as these coefficients alpha k are decaying, and that's what happens when f is analytic, they decay exponentially, then this is all bounded by some constant, and you get square root of d. This could be a very big constant, but a constant nevertheless. And so this proves that for a bunch of interesting problems, the classic discrepancy is square root d over m, or of, which immediately shows that, you know, the core set is, there is a bounded core set, and even within the streaming setting, you can get a bounded core set of, you know, by plugging in all the relevant materials. And just to finish with open problems, you know, these functions don't behave very well when you look at their Taylor expansion. So it's unclear what their discrepancy complexity is. Also, in the context of core sets, there are multiplicative core sets, and this talk was about additive. So it's interesting if something can be done for them with tools from discrepancy. I mean, maybe some have indirectly, but maybe in a more, you know, direct way. And finally, for the randomized setting, I'm not sure if this is tight. Maybe you can do something a little bit better. Okay. That's it. That is the end of my slide.
Thank you. So we have one question here, which is, I'm wondering what is known here for maintaining the core set under insertions and deletions of points.
Oh, that is a good question. So honestly, I'm not sure. I don't think, I never thought of it in the methods that I showed here. I don't think it's going to be a direct way of applying this. Because once you delete things, you know, insertions is, if it's just insertions, it's the streaming setting, right? But once you have deletions, I'm not sure. It could get complicated, I guess.
Okay, cool. Another open problem.
Yeah.
The next question is, does this approach help with some of the classical core set problems like k-means clustering?
So I tried. It does give, you can get something, but the other methods get better bounds than what I was able to get. So I guess mostly no, but a little bit.
Then there's a comment that there are no results, I guess, for courses in the community, in the computational geometry community, but they're mostly for insertions. Chandra is asking, so algorithmically for the learning problem, you would need to select the bad points. Is that tractable?
I guess the methods here are not constructive. So that is an open problem. It's not just, yeah.
So I guess Banachik's theorem can now be made constructive, but that would still be
No,
finding
it's
time
not
proportional
enough.
to it's not constructive enough, I guess. Yes.
Yeah, because I mean the proof goes through bounding tensor norms simultaneously for all dimensions.
Right. So I see. So the dimensions here are very large.
Yeah, and yeah, but that is an interesting problem. So for example, in sometimes I mean even so for kernel density estimation, for example, I can just share just a private experiment I did. You like I couldn't get these bounds of corsets, but even just with simple de-randomization techniques that in the worst case give you the same thing as random sampling, you know, for common data sets or well-behaved data set, you might get much more. I know it's definitely not the optimal thing, but I guess that's something that I guess would be interesting to explore. Like the average case behavior, it's kind of a somewhat easier problem that could be solvable.
I see. Okay. One more comment I think about corsets is that the bounds are generally not good for deletions.
Yeah.
Okay. Okay. Thanks. Great. It was a question whether we can give a 5-minute break. So we had a little side discussion and decided let's have a 5-minute break and resume at 3:10 Eastern time. So in 5 minutes, 10 minutes after the hour. And you, if you're there, do you want to share your slides now? So that we're ready. Hi, feel free to share your slides when you're ready.
Yeah.
Great. Okay. It is 10 minutes after the hour, so let's get started again. A brief break. So we'll have Peng Shang from Yale, who will talk to us about the really surprising for me application of methods developed for discrepancy theory in randomized experiment design.
Okay. Thank you so much for the introduction. I'm going to talk about our recent work on balancing covariates in randomized experiments using the Gram-Schmidt walk. This is a joint work with Chris Hashaw, Frederick Savage, and Dan Spielman. Okay. As you have already seen, in Nicole's talk, this Gram-Schmidt walk is a very beautiful algorithm in discrepancy theory developed by Bensal, Dadouche, Garg, and Lovett. Okay, in this talk, I will tell you how to apply the Gram-Schmidt walk, or more generally, how to apply discrepancy theory to improve randomized experimental design. Okay, let's just imagine that some lab has developed a new vaccine for COVID-19, and they are doing a clinical trial. They have multiple subjects, and they want to assign these subjects to 2 treatment groups. They think that whether the vaccine works may depend on some attributes or covariates of these subjects. For example, their age, gender, health conditions, and so on. So they want to balance these covariates between the 2 groups. Okay, you may think that this is a discrepancy problem. Yes. Well, there are some issues one need to deal with. So first, in discrepancy theory, the outputs are usually deterministic assignments, while in randomized experiments, people want random assignments. Okay, I will tell you a bit more later. The Gram-Schmidt walk outputs random assignments. Well, the second issue is that in CS, most time people are happy with large constants, while in randomized experiments, the most valuable resource is your subjects. Decreasing a factor 2 in the number of your subjects really means a lot. So people want small constants. Okay, in this talk, we consider Neyman-Rubin causal model, which is one of these popular models. We have n subjects, and we want to assign each subject to the treatment group or the control group. For each subject I, there are 2 potential outcomes. Each potential outcome corresponds to which group subject I is actually assigned to. Okay, we define AI to be the outcome if subject I is in the treatment group, and we define BI to be the outcome if subject I is in the control group. Okay, in this model, these AIs and BIs are fixed, and they are not affected by group assignments. We want to understand the causal effect for subject I. It is defined as AI minus BI, the difference between the two potential outcomes. However, the difficulty is that we can never observe both AI and BI. Since the subject I is either in the treatment group or he is in the control group, these two cannot happen simultaneously. So we never know the true value for subject level causal effect. What we are going to do is to estimate its average, and we hope the average could help us infer this subject level causal effect. Okay, let me define this problem in a more formal way. We have n subjects, and we want to output a random vector of assignments. We call it Z. Z has n dimensions, and each Zi is either -1 or 1. Okay, in this talk, we will assume that for each I, the probability that Zi being 1 is half, and the probability Zi being -1 is half. Okay, this doesn't mean that we assign everyone independently. Okay, when I say the design, I mean the distribution of this random vector Z. Okay, we have two vectors, A and B, for the two potential outcomes. Again, for each I, we can only observe one of A and BI. This assignment vector Z determines which potential outcomes we are going to observe and which potential outcomes will be missing. So if Zi is 1, we observe AI. If Zi is -1, we observe BI. And also, these AIs and BIs are fixed. So the only randomness resource in this problem is this random assignment vector Z. Okay, we want to estimate the average treatment effect. It is defined to be the sum of AI minus BI divided by N, and we denote this value by tau. We will use the observed outcomes to estimate this value tau. One natural estimator is the Howitz-Thompson estimator. Okay, we sum the observed outcomes AI over all the subjects I with Zi being 1, and we sum BI over all the subjects with Zi being -1. We take the difference between the two sums and we multiply it by 2 over n. Okay, here this constant 2 is related to our assumption that each Zi being 1 with probability half. Okay, we can check that the error of the estimator tau hat minus tau is 1 over n times mu transpose Z. Here mu equals A plus B corresponds to the potential outcomes, and we don't know mu. This estimator is unbiased. It means that the expectation of tau hat is tau. And we can also compute the variance of tau hat. It is 1 over n squared times mu transpose times the covariance of Z times mu. We want the variance of tau hat to be small. Okay, actually we want something more. We want the tails of tau hat minus tau to be sigma sub Gaussian. Okay, it means the tails of tau hat minus tau are dominated by the tails of a Gaussian random variable with standard deviation sigma. Okay, we want this constant sigma to be as small as possible, which would imply a narrow confidence interval, and which would imply a small number of subjects in experiments. So if we know nothing about these subjects, what we can really do is just assign everyone independently and uniformly. While in many situations, we know some attributes or covariates about these subjects. In our setting, each subject I is associated with the covariate vector xi. Xi has d dimensions and has Euclidean norm 1. We also define this covariate matrix capital X to be the matrix whose columns are x1, x2, ... xn. So covariates can help if this vector mu, which corresponds to potential outcomes, is close to the row space of X. An ideal case is that mu can be written as X transpose times some unknown vector beta. Then we get this variance of tau hat. I will multiply n squared on both sides just to make everything easier to look at. The variance of tau hat is beta transpose times the covariance matrix of xj times beta. Since we don't know this vector beta, we will upper bound this value by the 2 norm of this covariance matrix and the square 2 norm of beta. So why this is helpful? Well, the 2 norm of beta can be much smaller than the 2 norms of mu. Just imagine that we're in the regime that D is much smaller than N, and X transpose is a really tall matrix. Okay. We want to minimize the 2 norm of this covariance matrix of xj. So the Schmidt walk kind of solves this problem. Given n vectors, x1 ... xn, each has norm at most 1. The Schmidt walk outputs a random vector z with entries -1 or 1, such that xj is sigma subgaussian. By the definition of sigma subgaussian, we know that the covariance matrix of xj has 2 norm at most sigma squared. And for every unit vector theta, the tails of theta transpose xj are dominated by the tails of a Gaussian random variable with standard deviation sigma. Well, in the paper by Bensel, Dadouche, Gorg, and Lovett, they prove that sigma is roughly 6.3. Okay, I want to remind you of that. The Schmidt walk, together with the result by Dadouche, Gorg, Lovett, and Nicolau, provides a polytime algorithm for a theorem of Banach-Sig. So for their purpose, a constant subgaussian is sufficient. Well, in randomized experimental design, the most valuable resource is your subjects. If we could decrease a factor 2 in this sigma, then we will decrease a factor 4 in the number of subjects. So we really want this sigma to be as small as possible. We improved their analysis, and we show that xj is 1 subgaussian. But actually, this subgaussian constant sigma being 1 is tight. And we use some new ideas. I will tell you about it later. Okay. In the ideal case, mu equals to X transpose times beta. While in general, there is an error term epsilon, where epsilon is orthogonal to the row space of X. If we plug in this to the variance of tau hat, we get an extra term in this variance, which is epsilon transpose times the covariance matrix of Z times epsilon. Again, we don't know beta and epsilon, so we upper bound each term by the 2 norm of the covariance matrix times the squared 2 norm of the vector. Okay, we want both the covariance of xj and the covariance of z have a small 2 norm. However, there is we have an example that we can't minimize both these two terms simultaneously. So what we really do is to make a trade-off between these two terms. Okay, in our design, we choose a parameter phi between 0 and 1. We run the Gram-Schmidt walk with the input being this augmented matrix. It is square root phi x on the top of square root 1 minus phi identity. And we output a random vector z. So if we choose phi to be 0, then the input matrix is just the identity. The Gram-Schmidt walk outputs a random vector with the ID entries. So here we really make a trade-off between balancing covariance and whether the vector z being a random vector with ID entries. So what we show that the covariance matrix of xj has 2 norm at most 1 over phi, and the covariance of z has 2 norm at most 1 over 1 minus phi. More precisely, we show that the variance of tau hat can be upper bounded by the optimal value of this ridge regression. Okay, here this 1 over 1 minus phi corresponds to this term. This term really tells you how close are mu and x transpose beta. And this 1 over phi corresponds to this regularization term. Okay, what we really want to guarantee is that if the linear prediction is correct, it means that mu is close to x transpose beta. Then the covariance of xj is small, which means that the covariates are well balanced. We also want to guarantee that even if your linear prediction is wrong, we have the covariance of z is small, which means that z is close to a random vector with ID entries. Okay, now let me briefly show how the Gram-Schmidt walk works, and then I will give you some iteration on how to prove the one-step Gaussian. Okay, the input has n vectors, v1, v2, ... vn. Each has norm at most 1, and the algorithm maintains the vector z. The algorithm always guarantees z's entries are between -1 and 1. Once some entry of z becomes -1 or 1, we will never change it in the future. We call a vector vi is alive at iteration t if at iteration t the s entry of z has absolute value strictly smaller than 1. Otherwise, we call it frozen. So at iteration t, we first pick a pivot p, which is the largest index among all the alive vectors. And then we compute an update direction y, such that vy is the projection of vp onto the subspace, which is orthogonal to all alive vectors except the pivot vector vp. We then update z along the direction y by delta y, where delta is a random variable with mean 0. We always guarantee that at least one more entry of z becomes -1 or 1. So the whole algorithm has at most n iterations. Okay. Let me show you some iteration about one subgaussian. Okay, same as BDJL, we consider the moment generating function. By Markov inequality, you will get the tail bounds. Okay, according to the algorithm, they can be written as delta 1 y1 plus delta 2 y2 plus delta 3 y3 plus delta. This forms a martingale. And then same as BDJL, we break down all these iterations into phases. So each phase has all the iterations with the same p-weight. By the algorithm, each vyt is orthogonal to all the alive vectors except the p-weight vector vp. So if t and t prime are from different phases, then vyt is orthogonal to vyt prime. So these phases rarely decompose the whole subspace into orthogonal, decompose the whole space into orthogonal subspaces. So by this way, we could decompose our the inequality in our goal according to phases, and we only look at a single phase. The difficulty is that these vectors vyt, if they're from the same phase, then they are not orthogonal. Okay, let's look at a single phase, or let's just assume the algorithm has a has one phase. So Vn is always the p-weight. By reordering these input vectors, we could assume that the algorithm first phrase Vn minus 1, then Vn minus 2, then Vn minus 3, and so on. Last iteration, it phrase Vn. We do the Gram-Schmidt orthogonalization according to a reverse order, and we get an orthonormal basis, which are vectors b1, b2, ... bn. Okay, we will write everything in this inequality in terms of this orthonormal basis. Now we could write Vy1 to be the projection of Vn onto the direction Bn. And Vy2 is the projection of Vn onto the directions Bn and Bn minus 1. And Vy3 is the projection of Vn onto Bn, Bn minus 1, Bn minus 2, and so on. Okay, just for notation simplicity, we define alpha I to be the projection of Vn onto the direction Bn minus I plus 1. And we define beta I to be the projection of theta onto that direction. And now we have a very nice form here. We have that theta transpose Vyt, which is just alpha 1 beta 1 plus plus alpha t beta t. And the squared 2 norm of theta can be lower bounded by the sum of alpha I squared multiply the sum of beta I squared. And now the inequality in our goal becomes this inequality, which has some structures. So how do I prove this inequality? Let's look at the last iteration. So conditioned on all the iterations except the last one, we could write an explicit form for this conditional expectation. Well, instead of doing Taylor expansion, which may lose some constant, we managed to show the whole thing is maximized when alpha n and beta n are 0. Then we do a backward induction. Okay, Let me show you some future works. Actually, in this area, rarely not much is known. Okay, we prove the sub-Gaussian tail bounds. We prove that the probability tau hat minus tau bigger than lambda n is upper bounded by exp of something. Well, if tau hat minus tau is a standard Gaussian, then there actually had a lower order term. Well, in sense, most time people are okay if, without this lower order term. Well, in randomized experimental design, people do want this term, which would imply some better confidence interval. And we are working on online settings. So in this setting, all your subjects come one by one in online fashion, and we want to assign each subject upon their arrival. Also, we have some results on assign subjects to more than 2 treatment groups. Okay, I think you could also consider some other models. In this talk, we consider Neyman Ruby model. This is just one of these popular models. Okay, this is our paper and this is our code. I think that's all. Thank you.
Thanks a lot. Are there any questions? As I'm waiting, see if anyone else has a question. You sort of anticipated one question, which was what happens if you have more than 2 groups? Is there a variant of Gram-Schmidt type walk for that setting that you can use?
Oh, for more than 2 groups, we actually do a recursive assignments.
I see. So you kind of recursively use the Gram-Schmidt.
Yeah, and actually we only have a bound for the covariance. We don't have a tail bound yet.
Oh, so no bound for tails?
Yeah, for more than 2 groups.
For more than 2 groups. I see. Okay, that also sounds interesting. There's a question. Are there any applications of discrepancy in learning from observational data?
Oh, that's a good question. Yeah, actually, I don't know. I'm not an expert in randomized experiments, and actually, there are many things we don't know, and we think that this also means that there are many works people could do.
Just to make sure I understand, learning from observational data would be a setting where you can't really fully design the experiment yourself, I guess. I guess not. Okay, maybe this is better answered offline. Okay. Other questions? Okay, so let's move on to our final talk. Thank you, Peng.
Thank you.
And Aditya, feel free to set up, share your screen.
Is this visible?
Yeah, looks good. Looks good. So, right, for our final talk, Aditya Putokuchi, who are you in Rutgers now? Sorry.
I just graduated, yeah.
You just graduated. Congrats, nice. Will talk to us about discrepancy for, I guess, random and pseudo-random hypergraphs.
Okay, so hi everyone. Thanks for staying till the end. So yeah, I'm going to talk about hypergraph discrepancy in random and pseudo-random settings. Okay, so for the last time today, let's recall the definitions. H is a hypergraph. The vertex set is always n, and so I will denote a hypergraph by the set of its hyperedges. The problem setting is the following: you want to split again the you want to color the vertices red and blue in a way that every hyperedge is evenly or almost evenly split, and the best way to achieve such a splitting is called the discrepancy. Okay, so formally, so this is exactly the notation that Nikhil used in the first talk. Chi is a coloring of the vertex set, and 1 and -1 are just colors. For every edge, chi is the sum of all the colors of the vertices. It's just the amount of imbalance that's there in this edge. And the discrepancy of this coloring is the maximum imbalance that is there in any edge. And the discrepancy of the hypergraph is the minimum discrepancy you can achieve with any coloring. Okay, so that is just this is also another definition that was given. So I will use M to denote the incidence matrix of edge. So the rows are given by the edges and the columns are given by the vertices. And the corresponding entry is just whether or not the particular vertex is present in the edge. And discrepancies, it's a syntactic reformulation of discrepancy. It's a minimum L infinity norm of mx as x ranges over -1, 1 to the n. So far, so this is all of this recap. Something that will be relevant for us is the Beck-Fiala conjecture. More notation. I say that a hypergraph is T regular if the degree of every vertex is exactly T. That means every vertex is present in exactly T hyperedges. The Beck-Fiala conjecture says that every T regular hypergraph has discrepancy order square root T. And this is in particular independent of the number of vertices, number of edges, etc. And this seems to be a kind of hard conjecture for today's techniques. It seems that way at least. And here's some existing literature. And in this context, this is kind of partial progress towards the Beck-Fiala conjecture. The first is what's called the Beck-Fiala theorem. It says that every T regular hypergraph has discrepancy at most 2T minus 1. So the point is that you do actually get discrepancy, which is independent of the number of vertices, edges, etc. And I guess I'd like to pass on a remark, which is, so forget the fact that this has a linear dependence. So forget the fact that it's 2T minus 1 and not say T square. Can you get, and the Beck-Fiala theorem is really not simple to prove. And the question is, can you get a simple proof, quote unquote, simple proof of any bound that's independent of n edge? It just depends on T. Right. And so, yeah, but we have this kind of linear bound so far. And it can actually slightly be improved. And this is a short note by Bednarczyk and Helm, which says that you can knock 2 off this. So I know at least more than one way to do it. And this is a very short note. So every T regular hypergraph has discrepancy at most 2T minus 3. The current best known bound is by Boris book, which says every T regular hypergraph has discrepancy at most 2T minus log star T. So this theorem is really not easy at all. This is quite hard, and for the significant progress, but again, in terms of it's not much closer towards a Beck-Fiala conjecture. So this is the existing literature, and the focus of this talk is what happens if the hypergraph is random, right? So what do I mean by random? You fix the number of hyperedges, and there are two natural distributions of random hypergraphs. The first is every vertex, initially you have a bunch of empty hyperedges, and every vertex chooses T random edges to be a part of. So this way, for a given n and the size of the hypergraph, you get a random T regular hypergraph. So this is kind of in the Beck-Fiala setting. Another, I guess, slightly more natural one is every vertex edge incidence is IID Bernoulli. So every vertex is present in every edge with probability P independently. Okay. And what are the kind of questions we can ask over here is the discrepancy order square root T? You want the typical behavior of the discrepancy, and you want, in particular, you want to know if it's order square root T with high probability. So we've not they don't have the Beck-Fiala conjecture. So this is a meaningful question to ask. Something that's slightly more interesting is, can the discrepancy be lit law of square root t with high probability? Because these kind of statements are not true in general. Okay, so in what follows, I'll just give a brief overview of all the results in this area. The focus is mostly going to be on technique, so hopefully there's some takeaway from most results. Yeah, and for the most part, we'll be dealing with this. Every vertex is present in t randomly chosen hyperedges, and I'll talk a bit about the other one at the end. So this kind of random hypergraphs was initiated by Ezra and Lovett in 2016. And again, let's recall, this is the model of the hypergraph. You fix the number of hyperedges, and every vertex is present in t of these randomly chosen uniformly and independently. So this is the statement that was proved, which said that if the hypergraph is large enough, then the discrepancy of the hypergraph is order square root t log t with probability at least 1 minus exponential in t, right? So in that sense, this is much better than the worst case bounds we know, which is 2t minus log star t. It's still not square root t though. And moreover, the error probability depends on t. So for example, you get that for t equal to some, for a fixed t, you get that asymptotically 99.999 something fraction of hypergraphs have discrepancy order square root t log t. But you want statements like 100% of them asymptotically. Another remark is that this kind of statement is quite easy if t was at least as big as log n. Why is it easy? Because in this case, every edge has size order t, and it's an easy application of say Lova's local lemma to guarantee this kind of a discrepancy bound. And so really the main point was, when t was small, some edges will be much larger than others, and you want to handle this, right? And so the punchline here is that there will be large edges, but they're really mostly disjoint. So what do I mean by that? So this is the main lemma. So let S be the set of all the hyperedges of size at least 100t. Okay, then if in every edge you can delete one vertex, every large edge you can delete one vertex, so that after deleting they're all pairwise disjoint. So for the sake of coloring, you pretend that in the large edge whatever VE is guaranteed is not there. So I mean that causes only discrepancy of 1, which we can really which doesn't mean much to us in this regime, right? So what do we have here? We have a hypergraph with most edges at most 100t, and whatever is above 100t are disjoint. And it's a really nice exercise to show that the discrepancy of such a system is order square root t log t. And it's really like a nice exercise. And without giving much away at all, the hint is to first assume that there are no large disjoint edges. There's just the small edges. Okay, so this doesn't give anything away at all. And yeah, it's I recommend try, and yeah, it's there in the paper. Okay, so I'll talk a bit more. So that is what we had using just the basic combinatorial structure of the hypergraph. So here are some more ideas which are based on partial coloring, the partial coloring theorem again, which was mentioned by Nikhil in the first talk. I'll just remind you what this theorem is. So here's the hypothesis. You have a hypergraph H, and you have some constants. For every H, you have a constant satisfying some condition. So let's ignore this for now. But you have a hypergraph and you have a constant. You have a bunch of constants, and there is some fractional coloring -1 in of the vertices, such that firstly, according to this fractional coloring, every edge gets discrepancy square root of its size times this constant associated with it. And more importantly, half of the vertices get actual colorings. And so half of the vertices get colorings which are either 1 or -1. Okay. And of course, this can be found in polynomial time. So initially, I guess this was randomized polynomial, but then this is a very nice deterministic algorithm, which is actually different from whatever the original proof of this was. Okay. So what is the idea here? It is that you have a hypergraph, and you somehow set the constant which satisfy this, and you color half of the vertices properly, whereas the other half are some fractional. So now you just restrict your hypergraph to that subhypergraph where the vertices don't have proper colors, and you repeatedly apply. Of course, you need a bit of caveat. So because they already have some kind of a fractional coloring. So you want to remove that and then apply your new fractional coloring. But the point is that this theorem actually takes care of all that. So this is really the idea behind this partial coloring. So yeah, so let's look at this technical condition let's call it star. For every edge you have a constant such that summation of e to the minus c square over 16 is at most n over 4. So again, 16 and n over 4 are not really the important things here. And actually all that I want to kind of observe here is that you can actually have some edges to have zero discrepancy in the partial coloring. You can, again, this was also mentioned by Nikhil. So in omega n, for omega n many edges, you can set the constant so that they get zero discrepancy at the cost of, I guess, doubling the discrepancy of the others, which is not that much at all in this regime. So here's a slightly more recent result by Nikhil Bansal and Raghu Meka, which is the discrepancy of h is order square root t with probability 1 minus titlo of 1, provided t is at least a growing function of n, and this comes with an efficient algorithm too. Okay, so again, this litlo of 1 it goes to 0 as t goes to infinity, but we've gotten rid of this square root log n, and also we've gotten rid of this condition. The hypergraph need not be large anymore. You can have it work for small. So pictorially, the incidence matrix can be like this, and this is a regime where Ezra and Lovett's result did not apply, and this applies. And I really won't talk about the proof, but there is one interesting idea that I think can serve as a takeaway, and I also want to recall this much later. Really, the main step is to reduce this to the case where there are not that many more vertices. And here's a theorem. So informally, what is this theorem saying? So you have a hypergraph with n over log square n many hyperedges and a random t regular one. Then with high probability, this is what happens. You choose any discrepancy you want for every hyperedge as long as it's between 2t and t, minus 2t and 2t. You choose whatever discrepancy you want for every hyperedge, and there is a fractional coloring that guarantees exactly that discrepancy. So this is kind of used to reduce to the case, and so in words, this is what the theorem is saying. So every possible set of discrepancies is doable, but with fractional coloring, right? And this is kind of used to reduce the number of vertices, and then yeah, and the rest of the proof goes by a careful choice of this partial coloring, etc. But one thing I'd like to point out is, suppose this x naught was not a partial coloring but an actual coloring. Firstly, it would be done because this gives much more than what you want, and secondly, this kind of, it's a very nice thing to keep in mind. This one, I guess I'll recall this much later, and yeah. So that's all I wanted to say about, like, say, random hypergraphs. And now I'll talk about pseudo-random hypergraphs. Firstly, I'll describe a measure of pseudo-randomness of the hypergraph. So recall that this is the incidence matrix. So again, the rows are given by the edges and the columns are given by the vertices. And every entry is whether or not the corresponding vertex is present in the corresponding edge. And so this is really a quantity that might be of interest, which is lambda of the hypergraph is the maximum length of MV, where V ranges over all unit vectors orthogonal to all one's vector. Right? So for perspective, this is kind of reminiscent of the second eigenvalue of a graph, and it will be used in a similar way here. So this is so this lambda is kind of a measure of how quote unquote pseudo random the graph is. Sorry, the hypergraph is. Okay, and here is a statement. This is by me earlier this year, which says that if h is t regular, the hypergraph is t regular, then the discrepancy is order square root t plus lambda. This also comes as a deterministic algorithm, and this is a deterministic statement. There is no random hypergraph anymore. This is for any hypergraph, its discrepancy can be bounded as a function of its regularity and this parameter pseudo random. Like ideally, you don't want this to be there, but yeah. So so in cases where this does not depend on n and h, you get a similar kind of a statement. And as a corollary, you get this. It's that if h is random and the regularity is little of square root n, then with high probability, the discrepancy of h is actually order square root t. So you kind of verify Beck-Fiala conjecture again, as h is somewhat, if h is somewhat large. So the square root n is kind of a limitation of the proof technique here, and anyway, the largest is already handled before. So, and okay, and the reason I'm saying it's a corollary is pretty much the only reason it can be. It's that if h is again a random t regular with t little of square root n, then this lambda, whatever this lambda is order square root t. So this is like the second eigenvalue of, say, random regular graphs. And the proof also follows from the known technique. This is by Khan and Samredi in 89. So I won't talk about this at all. So this is the statement for the pseudo-random case. And I want to talk a bit about the proof ideas here. So here's the main idea. Suppose h was t regular, like how does a typical edge look like? What would be like a dream approach to proving the Beck-Fiala conjecture is that every edge, for example, has size big O of t, and really by Markov inequality, most edges do this, like 99% of edges do this anyway. And I guess more importantly is when you color the vertices using whatever partial coloring you want, and suppose you color half the vertices, you wish that half of every edge was colored. So in every stage, you don't accumulate discrepancy square root t, but it keeps reducing how much you accumulate. And yeah, applying this, applying the Lovett Meka partial coloring, you get that the discrepancy is bounded by order square root t. This is what you really want. But really, why this? I mean, this has been the hope for a long time. But the point is that, like, Nikhil actually gave an example where this really does not happen. So you cannot hope that when you color half the vertices, half of every edge is colored. But the real point is that if lambda is small, if this lambda is small, then that does happen. If you color half the vertices, you do color half of every edge, right? So again, here's the lemma, which again, fundamentally it says that if you take any subset of vertices, say alpha fraction of them, then most edges, you contain an alpha fraction of most edges. So, and how much you deviate from it depends on the pseudo-random parameter. And so if lambda was small, you contain an alpha fraction of all edges. Okay, so good. And so, right, like I said, if lambda was something like the second eigenvalue of a graph, this lemma is something like the expanded mixing lemma. Okay, so let's go back. So how is this helping us? How does a typical edge look like? It has size order t. So most edges do this anyway because of Markov. But now when you color half the vertices, half of most edges are colored too, and most edges do this too now. That's good. So now when you apply Lovett Meka, the total discrepancy is order square root t. But okay, there's a catch. There's only most edges. Discrepancy should hold for every edge. And this is where we use the extra feature of the partial coloring that, you know, in every atypical edge, which does not have either of these, you just set the constant to 0. And so that if in that round, that it's as if that edge does not exist. And the rest of the proof is essentially choosing the constant satisfying the partial coloring lemma. And yeah. And of course, as with the expanded mixing lemma, you need some kind of minimum size bound on the edge to guarantee the pseudo-randomness lemma. And this works only as long as the edge size is order lambda. And if that does not happen, just give up. And that's where you get the extra lambda in the bound. Okay. So this is pretty much, so this contains all the proof ideas. It's just making, just choosing these things formal. Good. And here are some more results. So the previous two results were algorithmic, and I'll talk about a bunch of non-algorithmic results, but they prove some things much stronger. So here's an idea. Suppose M has many randomly chosen columns. Think of this as the incidence matrix of a hypergraph, and say T regular hypergraph 2. And suppose it has many randomly chosen columns. You think that when you take all +1, -1 combinations of the columns, you get all the vectors in a certain ball. Like more precisely, if you take a random +1, -1 combination of these columns, you think that My looks like an isotropic Gaussian with mean 0, right? Because the mean of every edge is 0. It looks like is a very vague thing. And if it looks like an isotropic Gaussian, you think that something like this would happen. The probability that My lies in whatever interval you want, it's as if a probability that an isotropic Gaussian lies in whatever interval you want. And the main point is that this is non-zero. And if you can prove this kind of a statement, you get that with high probability, the discrepancy is actually at most 2. Right, and so yeah, this is kind of similar to Meka, where this kind of thing is guaranteed with fractional colorings. But if you have many more colorings, something similar in spirit is guaranteed with proper colorings. And you prove this so-called local limit theorem by using ideas which are similar to those in Kuperberg, Lovett, and Pilet. And using this, I just want to mention some results. If h is smaller than n to the 1/3 with some logarithmic factors, then the discrepancy is actually at most 2. And this goes by proving such a local limit theorem. Around the same time, using more or less the same ideas, you also get that if h is order much less than square root n, then the discrepancy is at most 1, or okay, this might be 2, but yeah, the discrepancy is at most 2 for sure. This looks like an improvement of this, except here the model of h is different. Here we are in the case where every edge vertex incidence is chosen with independently with some probability. So, and again, so it was an open problem by Hoburg and Roth, was saying if h was actually slightly larger, do you also get this kind of a result? And this again, this was like I think this is a preprint available on arXiv, which says that you do get the discrepancies at most 2. And the ideas here, like as the title suggests, are more related to the second moment method. And here's the idea: let E1 to EH be the edges and fix any coloring. Then the probability that every edge gets discrepancy 2 with respect to this coloring is just the product of the probability that each of them get discrepancy 2. Because again, if you're picking every vertex edge incidence independently, these things are independent. And so, the expected number of them is also large, and the rest of the proof is just a very, very lengthy and careful second moment calculation to show that this is kind of what you expect. And so these are kind of most of the results in this area. Here are some open problems. So this is a conjecture. So you're back in the case where every vertex is in T random hyperedges. And suppose H was so that the size of H is order n over log n, then the discrepancy of H is actually 1. I tried adapting the second moment method from the previous slide, but it was much harder, and I didn't know. There should be a cleaner way to do this. In particular, none of the algorithmizing any of the last 3 results I mentioned would be very interesting, because currently they just show by Fourier, they just essentially show, they're essentially counting results. And another thing related to pseudo-random hypergraphs is if you have T regular matrices with 0, 1 entries, you can bound the discrepancy in terms of spectral information. Can you do it if it's just 0, 1, -1 entries? So this is, I guess, this is a special case of, say, the Komlosh conjecture for orthogonal vectors. So yeah, so these are 3 problems that I think are nice, and yeah, and that's it. Yeah, thank you for listening. And do you have any questions?
Thanks, great. Please feel free to ask questions. In the meantime, I'll ask one speculative type question, which is, so since you have this result, it basically says that for pseudo-random hypergraphs, you get this, where I guess I define pseudo-randomness as lambda is at most square root of t. Then for such hypergraphs, you can prove the Beck-Fiala conjecture. So it's kind of tempting to now fantasize about some sort of pseudo-randomness versus structure kind of decomposition as an approach to the conjecture. But I mean, I know that if you could do this, you would probably claim a proof, but can you speculate on that, or do you know there's a good reason why this cannot work?
Yeah, so because so one reason that I can think of why it doesn't work, which was by my after I initially jumped on this idea, is that the pseudo-randomness result for general graphs decay quite badly, right? So the regularity lemma is it's quite bad in terms of. Okay, so here's a concrete question. Suppose we know the Beck-Fiala conjecture. So again, let's restrict ourselves to the case where there are n hyperedges, right? N vertices and order n hyperedges. If I guaranteed order n regularity, you can prove the Beck-Fiala conjecture. That's the usual partial. So can you do it for say n over log n? So this is a regime where you have some kind of structure with pseudo randomness, workable quantities in graphs. So I don't even know this.
I see. Okay. Okay, we have some other questions. I think the first one. So okay, at least I started first. Do things become easier if we assume uniform and regular hypergraphs?
It's really the same proof again. So setting the large edges to 0 is just something you have to deal with anyway. So I don't think it's much easier.
Okay.
You get order square root t log t in the worst case, but again, so if all of this is assuming you want to beat that.
Right. So yeah, I guess one comment I had was right. If you assume uniform and regular, then you can just use a Lovett local lemma. But
yeah,
if you want to do better than that, and that gives you square root of t log t. But if you want to do better than that, I guess you're saying it's not clear.
Yeah, you have to deal with large edges at some point in the partial coloring. So.
Okay, and Chris Herschel has a question. Minor clarifying question: can Beck-Fiala always be reduced to the size of h is at most n over log n setting, or do we lose something in this reduction?
I mean, so for random one, or is it for the worst one?
Yeah, I'm not sure if this is for random or worst case. Is there? Sorry, does the reduction use randomness?
The Bansal and Meka one? Yeah, it does.
I see.
Yeah,
so it's not clear if in the worst case you can always reduce it to that n over log n.
But in worst case, you can always assume h is n, right, by the linear algebraic trick.
Yeah, so by linear, right, yeah.
Yeah, but right. So it's really about random that you can't use that. What you might be left, the columns you might be left may not be random.
Right. So there's a general linear algebraic trick which allows you to basically assume that wait, does that work in the right direction? I guess you can assume that the number of columns is at most the number of edges. I think, like the number of elements is at most the number of edges.
Right.
By linear algebra, but that's like a worst case reduction. So if you want to prove statements for random graphs, it doesn't reduce like random to random with the same distribution. So it's not clear. It's useful there, but it's potentially useful for the worst case problem. But that's pretty hard, I guess. Okay. Another question two questions. Nice. From Callum. What do you think the correct dependence on lambda is in your theorem? That is, do you think that the appropriate lambda might yield upper bounds better than root t?
And so I mean, like the ideal dependence is nothing. Lambda shouldn't even be there.
Right.
But yeah, so that's another thing I tried for a bit, like to improve at least in independence in lambda without, it's not the correct one, but yeah.
Okay. And Ainesh is asking, what is the precise open problem when obtaining spectral bounds for minus plus 1 and 0 hypergraphs?
So I really don't know, but for example, like here's a concrete open question. Suppose you have a bunch of almost orthogonal 0, 1, -1 vectors where you have at most t, which support at most t. So yeah, can you then prove them? So yeah, the almost orthogonal is the spectral information that you have.
Right. Nikhil, didn't you have some question about that something similar? Am I imagining things? Something with okay, never mind. Something with where the sets intersect in only a small number of elements, maybe.
Right.
Never mind. I guess not for live broadcast. Okay. Excellent. So thanks to the speakers for all the great talks, except the second speaker. And thanks for everyone staying for a number of hours until now. And I think we're going to wrap it up here. We'll eventually have slides on the website and hopefully a recording. I think the live stream should stay on YouTube, actually. Okay, thanks.
Thank you.
Thanks. Okay, so I'll end the meeting now. Bye, everyone.
Bye.